Hello everyone again and welcome to this new presentation on AI and machine learning. Starting with module 1, data preprocessing and feature engineering, which is the preprocessing of the input data, the normalization so that different values won't be so much far from each other, so they need to be normalized at a specific scale with a reference point, so not too high and too low, and feature engineering, also another name for that. So data preprocessing and feature engineering, the features are the input, by the way, these are the inputs that are used to predict the target, which is the outcome, okay? So data preprocessing and feature engineering are critical stages in the machine learning pipeline. They transform raw data into structured, informative representation that improve model accuracy, which means getting the correct result, the expected human-like result for a prediction. Stability, a stable model, it means that it would reproduce the same result under different circumstances based on the same input, the same feature values, and generalization capability. So if it gets new inputs, based on the all inputs, it can get an accurate outcome. Okay, so based on a specific data set, a specific number of features, based on that, based on these data sets or a data set that it had swallowed and digested, it can produce an accurate result. Although it would be a new form of input that's not already in the database. This is what it's called generalization. So no matter what the input would be, it can predict the correct value at the output. Data preparation ensures that data sets are clean, they are consistent, so there are no parodies or inconsistencies, and numerically suitable for learning algorithms. Because we cannot have, for example, characters. Even characters or like answers such as yes and no should be digitized, should be coded or encoded as, for example, for yes, you should have 1. For no, you should have 0, because computers can deal with numbers, with numericals, not with characters. Normalization and standardization. Machine learning algorithms are often sensitive to feature scale. Two common techniques are used. The min-max normalization, so normalization of values based on the minimum and the maximum, and this is how it works. So normalization rescales, this is a rescaling, okay? Features into a fixed interval, just like quantization in analog to digital conversion. If you're familiar in numerical or digital communications, you have a conversion from an analog signal into a digital signal. It should be based on a fixed scalar, a fixed number of levels. And these level values would be coded by 0001, 1011, for example. For each level, like whenever the signal passes through or is close to one of these levels, it would be captured, okay, and recorded in such way. So, but I digress here. Normalization here for the features rescales the features into a fixed interval, typically from 0 to 1. This is how it works, so that we would have, and especially for the deep learning or for the neural networks, because for a value greater than or equal to 0.5, the neuron, the perceptron, would be activated. For less than that, it would not be activated. This is the point here. So x normalized is equal to x, which is the current value, minus the minimum value from the entire set, divided by the difference between the maximum value and the minimum value. So x minus x min divided by x max minus x min. This would give you a value between 0 and 1. X would be the original value. X min and x max are minimum and maximum values of the feature. This preserves relative relationships but changes the magnitude. Second method is the standardization, or also called z-score scaling. Standardization transforms data to zero mean and unit variance. Okay, so Z is equal to X minus mu, which is the mean of the feature, divided by sigma, which is the standard deviation. We're going to see the formula of standard deviation in a moment. Now, mu, which is the mean of the feature, is the sum of all the values of the features. Okay, I'm sorry. It is the sum of all the values of this one feature divided by the number of these specimen, of these samples. So it is the sum of all the values, okay, all the values for different samples, divided by the number of the samples. It would give you mu, which is the mean of the feature. Standard deviation has a different formula. We're going to get that in the next slide. So standardization is preferred for algorithms assuming Gaussian distributions, for example, SVM, which is supporting vector machines for the logistic regression. So standard deviation, or SCD-dev, is given by 1 over n, which is the number of samples, multiplied by the sum of the difference between each value for each sample minus the mean, the entire mean for the set, square. Okay, so the first value, let's say the first value is 2, minus the mean of the values is 5, so 2 minus 5 square, plus the second value would be, let's say, 7. So 7 minus mu, which is the mean, again the mean is 5, 7 minus 5, 2 square. You add up all for all the values of this feature. Okay, then you divide by the number of samples for this very same feature. So again, standardization is preferred for algorithms such as for those working with Gaussian distributions such as SVM and logistic regression, supporting vector machines and logistic regression. Outlier detection. Outliers are abnormal observations that can distort model training. So what are these outliers? For example, let's say you have values 5, 10, 10,000, okay? Then you have one value such as 1,000,000, okay? And you are like measuring kind of the difference of pressure or like the magnitude of an explosion. I don't know. It might be anything within a model that's trying to detect or like predict, for example, the magnitude of an explosion. Let's assume that. The magnitude in certain conditions can be infinity. Okay, you cannot have that. It will distort your model. So you need to remove such value from the set. Otherwise, the model cannot be trained. Why? Because it will affect the normalization, because then you would be normalizing against a very large value that is way above the mean for the entire set, like the acceptable mean. Okay, it is way off the chart. It can be distorting the z-score. So we need to get rid of these values. Or, for example, if a value is not defined, okay, not available, this would be more than a 0 value. It would be null, okay? So you cannot have that. But here we are more talking about the values that are way off the chart, way off the normal, the mean of the other values within a feature. So in order to detect these values that are the outliers, that are like the intrusive values within the set, a data point would be considered as an outlier if Zi, so like the modulo or the absolute value of the z-score is equal to xi minus mu, which is again, xi is the current feature value, minus mu, which is the mean, divided by sigma, which is the standard deviation, or 1 over n times sigma from I equal 1 to n of xi minus mu square. If that is greater than k, okay, typically with k equals 3, it means that the value is way off the chart. It should be removed and not counted in, so that the model can be well trained and actually produce the expected values. Interquartile range, IQR. IQR is given by Q3 minus Q1. Outliers satisfy the following. X is less than Q1 minus 1.5 IQR. Okay, or x would be greater than Q3, okay, plus 1.5 IQR. In other words, that the value is way off this interval, whether it is way less or way more, okay, based on this kind of scalar. Where Q1 and Q3 are the first and the third quartiles. The first quartile, so 1/4 of the value, okay, the overall value. And the third quartile, so it would be the third of the maximum value. Feature scaling. Distance-based algorithms require comparable feature magnitudes. So, and this is due to the fact that for some models, the values would be so close to each other, okay? So you need to scale them. You need to blow them up in order to be able to detect the difference between these values. So it's like when you have points drawn very close to each other on an image on Windows, okay? You need to get the magnifier and to magnify these points. And this is when the distance, the actual length between these different points would be clear, would be measurable and quantized. Otherwise, on a lower scale, they might seem to be very close to each other, as if forming, as if colliding on the same location, as if they were the same point, okay? We cannot deal with that. In order for us to actually detect the difference, okay, between, or like the distance, different distances between each 2 points within such a model, you need to blow it up. You need to magnify it, and this is why we need a scaler, where the values would be blown up so as to be able to discern the difference, okay, between these different dots, different values, the different distances, because based on that differential of distances, based on the difference of distance between all of these different points, this is how you can get, okay, which value belongs to what result, okay? So let's say you have in a KNN classifier, we're going to explain that, okay? Let's say you have, we are trying to get in a model, you have different specimen, one belonging to a dog, another for a cat. And this is based on the length of the fur, correct? So the length of the fur wouldn't be that different. So the dots would be close to each other. So you have the length of the fur here, or here, let's say, okay? And here we're gonna get if it's a dog or a cat. Dog to the left, cat to the right, let's say, okay? So that would be these dots. Based on the length of the fur, you're gonna predict whether it's a dog and a cat. This would be a classifier, okay? Logistic classifier, I think. Yeah. So these dots may be very close to each other. So when you blow them up, this is where you would be able to identify the difference between, okay, these belong to a dog, the others belong to a cat. General scaling transformation is given by x prime is equal to ax, which is, the multiplier. This would be the slope for the line of the scalar, okay, which is equal to rise over run, by the way, and b is the y-intercept. Okay, common methods are min-max scaling, standard scaling, robust scaling, which is based on the median. Now, scaling improves convergence, speed, and gradient-based optimization. Now, to give you an image on what it would be like, so let's say this is ax plus b, which is what the equation, actually the plotting of this line equation. Now, a is rise over run. So let's say this line here is rising by 1 as it travels to horizontally. That would be 1 over 2, rise over run, x plus b. B is the y-intercept. So let's say this is x and y, okay? So b is the y-intercept. Where does this line cut the y-axis? Let's say it cuts it at y equal 1. So that equation would become 1/2 x plus 1. That would be this equation of the standard scalar, or like this kind of the general scalar. Feature engineering. Feature engineering transforms raw variables into informative predictors. All right? Now, one of the types of engineering is encoding a value of yes and no into 1 and 0. So transforming characters or character values for a feature into a digital numerical value that can be processed by a machine learning algorithm. Now, at first, it starts with feature extraction. Feature extraction constructs new variables from existing data. Given input vector, x equal x1, x2 all the way to xn, t. T is the transpose, which means that this becomes like this, okay? Like an input. Transpose means that the vector x becomes x1, x2, the vertical vector all the way to xn, like this. That would be the input to the model. A transformation function produces z equal f of x. Now, examples include statistical descriptors such as the mean, the variance, frequency domain features, FFT coefficients, okay, like a fast Fourier transform, which transforms a signal from time domain into a frequency domain, into the frequency domain. So you have, let's say, the sine wave. It is described in the time domain, okay, like x equal a sine omega of t, or 2 pi ft. It can be transformed into the frequency domain, which is a exponential minus j omega t, which is simply the amplitude and the frequency value. So from a time domain into the frequency domain. In the frequency domain, this amplitude, this sinusoidal, becomes simply a pulse value, which is describing the amplitude of the signal, and its frequency would be on the x-axis. Its frequency value would be on the x-axis. Okay. Now, polynomial expansion example: phi of x is equal to 1, x squared, x3, which enables nonlinear modeling using linear algorithms. Okay, so these would be different examples for the transformation function. Now, to give you an example on the FFT, so let's say you have this signal, which is a sine wave. This is in the time domain, and this is the amplitude. So let's say the amplitude here is A, amplitude, and this would be the time domain. So you have here pi and 2 pi for a full cycle. So to describe it in the frequency domain, this becomes A exponential minus j omega t, where omega is the pulsation. So actually, in the frequency domain, 2 pi f, j omega is 2 pi f, so it would be drawn like this. So that is the frequency. The frequency is 1 over time, correct? So let's say in such case, it is 1 over 2 pi, let's say, okay? Here, 1 over 2 pi, that's the frequency, and the amplitude is A. So this would be the frequency domain representation. So from a full wave, it became like a spike on this, like an impulse on this frequency domain representation. Here in this example, we're seeing 3, 2, 10, 6. Let's say these are different values for a feature, okay? Of course, they would be way more than that. And these would be on the row side, like in the row direction, not in the vertical or in the column direction. In the column direction, you'd have different features. Here, you would have, for each feature, 3, 2, 10, 6. So they would be vertical, not horizontal, but for the sake of the example here. So 3, 2, 10, 6. Let's find the x normalized. That would be equal to x, which is the current value, that is 3, minus x min. The minimum value here is 2, divided by x max minus x min, which is the maximum is 10, minus 2, 8. Okay, so that would be 3 minus 2, 1 over 8, or 1 over 8. For the second value, x minus x min, that would be 2 minus 2, because the x min is 2, which is 0, divided by x max minus x min, divided by 8, so it would be 0. Then here 10, x minus x min, so it would be 8, divided by x max minus x min, which is also 8, because the x max is the actually the x here, so it gives you 1. Finally, for 6, it's 1/2. Now, for the z value, that would be x minus mu, which is the mean, divided by sigma, which is the standard deviation. The mean is 5.25. Standard deviation, here you evaluate for each x, so that would be 3 minus 5, the mean, square, divided by 1 over n, which is 4, which is the sigma here, times xi minus mu square, which is 3 minus mu, 5.25 square. Okay, so you evaluate for each value, and this is how you get finally z-score for each of the values of the feature. Dimensionality reduction. High dimensional data sets suffer from the curse of dimensionality, which means that you would have values that are way above the norm, so they would be outliers, so to speak, and if they are kept, they would mess up your model. Now, dimensionality reduction, at times you have more than one value like that, you cannot get rid of them all. So we need to reduce these dimensions. Dimensionality reduction seeks a lower dimensional representation so that the model can be better worked with. So that if you have very large values, okay, you can rescale them by normalization, for example, into smaller values that are much easier and more practical for the system, for the model to work with. So that the redimensioned representation would be Z is equal to W, which is the projection matrix, okay? T is transposition, the transpose of the matrix. So the vector that would be like that, it would stand like this vertically, multiplied by X, which is the value for each feature, okay? Here you would get the benefits would be reduced computational cost, so the computation would be lesser instead of having to compute much larger values. Noise suppression for the spike patterns, because you would have values that are way above the norm, so you can like pull them much down. They would be much closer to the average. And an improved generalization, which makes any new value much adaptive and more predictable. Okay, so it can handle new values and it can predict new values. That would be the improved generalization. Principal component analysis, or PCA. PCA finds orthogonal directions maximizing data variance. Okay, so we go through step 1, which is mean centering. Mean centering actually replaces the value of a feature with its distance from the mean. So for each specimen, for each sample of that feature, you take the sample value minus the mean, which is the sum of all values for that feature divided by the number of samples, by all the number of de relevés in French, which is all the specimens that have been taken, okay, on the row. So all of these samples that have been taken within the data set. So sum of values divided by number of samples give you the mu, which is the mean, and mean centering is given by, for each feature value, for each value of a feature, minus mu, which is the mean that distance would replace the original value for the feature as being the actual value for that feature. Step 2, covariance matrix. This is given by 1 over n, the number of samples, sigma, the sum of xi, which is again the mean centering value, the distance from the feature value to actually the mean, multiplied by the transpose of the vector, multiplied by the transpose of the transpose of all the sets of the mean centered values. Eigenvalue decomposition. So CVK is equal to lambda k VK, with VK is the principal components that are the covariance matrix and the actual mean centered value multiplied by lambda k, which is the variance explained. Projection, data projected onto first m components. Z is equal to VMT multiplied by x, the current value. So variance explained ratio. Explained variance is given by sigma k equal 1 to m lambda k divided by sigma k equal 1 to n lambda k. Data set splitting. Proper data set partitioning ensures unbiased evaluation. Okay? Now, you have training, validation, and test set, which means that the data set would be split into 3. A part for the training, okay? So a part to train the model, meaning that based on that, the model would be trained. So he would learn from the feature values, from the different feature values or features values, because there would be more than one feature definitely. He would learn how to predict the outcome. Now the validation is used so that to compare, or so as to compare between the training, okay, the training set and the validation set. The validation set would be a set of features that is left to the side, and it would be like to validate if actually the prediction is getting the correct outcome, okay? And the test set, finally, almost like the validation, okay? So the test set is a part of the set from the data which is not used for the training, but it's actually for testing, meaning that you test based on the features and you check the outcome that is obtained through the model. So we've tested, okay, the AI, the machine learning model, have predicted an outcome. Let's say the outcome was 1.5 as a value for whatever, okay, as a value for something, or 15, or whatever number you want to come. Okay, so the value that has come up, that the model has come up with, is 1.5. Okay, then the algorithm would look at the actual value. This is not the predicted value, this is the actual outcome from the set itself, from the test set. Let's say the outcome is 1.7. Okay, so how much the accuracy would be? It would be the difference, 1.5 minus 1.7, okay, divided, or this would be the error margin, okay, 1.5 minus 1.7 divided by 1.7, okay, we check how much is the error margin, and the accuracy would be 1 minus the error margin, okay? So typical ratios, you have 70% that would be the training model, okay, that is used for the model training, for the learning. Then the validation set for the hyperparameter tuning, for the parameters that have like very large values. And finally the test, that would be the final evaluation to see the precision and the accuracy of the system. So D equal D train, or the entire data set, okay, is actually formed of 70%, which is the D training part, plus the 15%, which is the validation part, plus the 15%, other 15%, which is the test part. All of these three would form like the total data set. Cross-validation. Cross-validation improves robustness by repeatedly splitting data. Okay, you have k-fold cross-validation, dataset divided into k-folds. Training occurs k times, like each k cycle, you would have a training, okay? Now, the error margin would be, or the error for the cross-validation would be equal to 1 over k sigma EI, okay? So EI is the validation error for each time you have a cross-validation. In other words, the validation occurs each k cycle. That would give you the resolution for the model, okay? So let's say you have a training of k times and k is very large, you'd have an enormous accuracy. Not always, okay? You might have overfitting, but you have, so error of the cross validation is given by 1 over k, 1 over the number of times of cross validation, multiplied by the sum of all the validation errors of fold I. Common choice would be k equal 5 or k equal 10 for cross validations. Bias variance trade-off. Cross validation estimates generalization error. So E generalized is equal to EXY, approximately PLFXY, okay? So it prevents overfitting, again, low training error, high test error, okay? Low training error overfitting means that when you have too many values that you're trying to fit the model around, this would be overfitting. So not too many degrees of freedom. So it has been so much trained over the current values of the data set to the point that any new value, okay, it can no longer predict, okay? So it only knows what it has been fed, to the point that it can no longer learn anything new. It can no longer predict based on new data. So it would give you based on the old data, okay? So in other words, like the model, the curve has been overfitted to the features in a way that it had gotten much further, okay, from any new value that you would give it. So it can give you erroneous value with a very little accuracy. That would give you, actually, the outcome for that would be a high test error. Underfitting. So in underfitting, there would be a high bias. So to give you an example, let's say you have these samples here, okay? These are different samples. And the underfitting would be like that. Okay, this is not correct because these values are very far from the slope of, let's say it's a linear system, okay? It's a linear regression, okay? So all the values are very far from the actual slope, so it would give you a low accuracy. Summary: data pre-processing and feature engineering transform raw data sets into optimized learning representations through scaling, which means that you are changing the value in a way that is more fitting and distinguishable by the models so as to ascertain which value belongs to which outcome, so to speak. Cleaning, data cleaning, for example, can be removing not available data or null data that are not fitting, or zeros at times that should not be considered as valid inputs. And transformation, which would be like normalization, standard scaling, and dimensionality reduction. Proper data set splitting and cross-validation ensures reliable performance by the model estimation and strong model generalization. Generalization means that when you have new features, you can get an accurate outcome being predicted based on these new inputs that are being fed to the system. Supervised learning. Supervised learning refers to machine learning methods where a model learns a mapping between input variables and known target outputs. And these outputs, the different types of outputs that you can get, are already known. So they are expected. that either you would have this outcome or that outcome or that outcome. So these are called also the labels. For example, you would have a target such as yes or no, or a different category of animals that would be the target. Okay, this is the main difference between supervised learning and unsupervised learning, where you would have different types of targets that are not actually known, but they are distinguished based on these different inputs. Now, given a data set where xi is the feature and yi is the label, which is the final outcome. For I equal 1 to n, where n is the total number of values for the features, where xi in r to the power of d represents real number within a dimension d. That's a feature vector. And yi denotes the labels or the outcomes or continuous targets. The objective is to learn a function f is x going to y. So y is predicted based on x that generalizes well to unseen data. Regression algorithms. Regression models predict continuous numerical outputs. Now, linear regression assumes a linear relationship between features and target, which means that the prediction function is actually a line equation. For instance, as an example, let's say you are measuring or trying to predict the price of housing based on the proximity to the downtown center, okay, city center. So you notice that there would be a linear relationship between both of these, where the proximity, or in other words, the decrease of the distance between the location of the downtown center and your current location would imply in a direction, in a direct proportional linear way, the increase of the house pricing. That would be a line equation. It would be given by y, which is the predicted value, is equal to w to the power of t, which is the transpose of the weight vector, okay, multiplied by x, which is the feature vector, the features, plus b, which is the bias or the y-intercept. Now again, that relationship would be given by this way, okay? It can be represented in this way. So that would be the line equation, w to the power of t, or that's not a power, that's the transpose of w vector multiplied by x plus b, b being the bias, but here, like geometrically or analytically, that would be the y-intercept, or the point at which this line intercepts the y-axis. So that would be here, for example, let's say the distance is 2, okay, and w, which is multiplied by x, is actually the slope of the line, which is equal to rise over run. So for each two distances or two cases crossed horizontally, you have a rise, a vertical rise of 1, okay? So y in such case would be equal to 1 over 2, this is rise over run, multiplied by x plus b, which is the y-intercept. In this case, it is 2. That would be the linear regression equation of prediction. Here in this illustration, we see the different data points that are actually the different samples of a data set. Let's say these data points are the expected height of something based on a feature. I don't know. Let's say the feature would be the type, or not the type. Yeah, like not the... let's say this is the distance from the edge of the city, not the proximity. Okay, so as you go away from the edge of the city, you get closer to the city center, so to speak. Okay, the price or the house pricing increases. That would be something like that. Now this is the prediction line, which is the linear regression. That is the prediction function, so to speak. And you see, as you notice, the data points, the actual data is not exactly on the line. So you have an error margin. That error margin is due to the fact that you have the line, yes, it is at proximity of these points, but whenever the point is a little bit further from the line, that would give you a margin error, a margin of error. So that would be the distance between actually this point and the elevation of the line, the regression line at that location. So for this point, for example, that would be this distance. This is the error margin for this value. Now, the overall error margin can be evaluated in different ways. So, for example, the mean error, not the square one, because we have different types. MAE, it's called. It's given by 1 over n, which is the number of samples, multiplied by sigma, the distance between the actual value and the predicted value. Okay? xi minus, or actually yi minus y predicted, okay, and you add it all up, you get the average error, okay, the mean average error. That's the function. Now, the matrix form is given by y equal xw plus b. So you have y is the vector of predictions, the vector of outcomes. Let's say you have white, blue, something. Let's say it's a color. Of course, it would be encoded with a number. Is given by x, which is the vector of features. So 0, 1, 2, 0, 1, different values multiplied by w, which is the weight. Actually, yeah, x is the feature value. So w is the weight, plus b, which is the bias, especially used in machine learning algorithm of neural networks. Now, the loss function, we have different loss functions. Let's start with the mean squared error. Mean squared error is equal to 1 divided by n, which is the total number of samples, multiplied by the sum of yi minus y predicted squared for each y. So going back to the curve, not the curve, actually the linear regression line. So it is 1 over n, n being the number of samples here, the total number of red dots, multiplied by sum of x, or sorry, yi minus y predicted, so distance from here to here, square, plus distance from here to here, square, all the way. For each point, the distance between that point, the elevation of that point and the predicted point, square, you add them all up, you divide them by n, which is the total number of samples, and this is how you get the mean squared error, okay, which is meant to magnify the error value so as to explicitly express how much the error is, because if the values are so close to each other, you cannot get that magnification, okay? The point, predicted point, would be colliding with the actual value point. Closed form solution, normal equation is given by w is equal to transpose value of x times x, which is the original matrix, times the transport value, minus 1, which is the inverse of that product, multiplied by x of t by the transpose of x, multiplied by y, which is the predicted value. Here in this representation, you see that you have the line of prediction and the different values that are the actual values. By the way, the fitting of the prediction function is by trying to rotate this line as much as possible in a way so as to minimize the error margin, so as to minimize the errors, which is the gap between the actual values for each scenario and the predicted value based on this line. So this is why we try to fit this line in a way to make it as close as possible to different values. Of course, you're still going to have error gaps. Now, again, the mean squared error is 1 over n, which is total number of dots here, black dots, multiplied by the sum of yi minus y square. Okay, so for each predicted value, the distance between that and the line square. You add it all up, you divide them by n. This is how we get the mean squared error. Polynomial regression. Polynomial regression models nonlinear relationships by expanding features. So instead of having a line as a prediction equation, you have a nonlinear relationship, which means that the prediction would be a curve of second degree order, third degree order, depending on the scenario. So the equation would be like a parabola or an exponential curve given by, for example, y equal w0 plus w1x plus w2x squared, etc., based on the degree to which you are aiming in order to fit the values to be predicted. Feature transformation, phi of x, is given by 1x, x squared, xn, so the feature would be squared or elevated to a specific order, okay, depending on what we're talking about, depending on, again, the relationship between the input and the label. The model remains linear in parameters, but non-linear in input space. So, for instance, here you have, let's say, the values are distributed in this way. Now, in such case, a linear regression will not make it. It would not be fitting for such a type of values, okay? You would rather need a curve like this one here in order to fit the values to be predicted, okay? So it would be of a second order instead of, at least of a second order, instead of having a line. Another type is the ridge regression or L2 regularization. Ridge regression penalizes large weights. So it affects weights that are very large. It dims them down. JW is given by 1 over n, sigma I equal 1 to n, yi minus yi square, which is the difference between the actual value and the predicted value square. Yi is the predicted value and yi hat, I think it is the actual value, plus lambda w square. Here is where you get, like, it is like the mean square error, except you add to it the lambda w in order to target the very large values, to penalize them as being a high factor that affects the error margin of the entire function. Where lambda controls regularization strength effect, okay, reduces overfitting and shrinks coefficients smoothly. Lasso regression, L1 regularization of level 1. Lasso introduces sparsity, which is given by 1 over n sigma I equal 1 to n, yi minus y hat I square, again, this is the mean squared error, plus lambda w1. So it adds a value to the error in order to add sparsity, where w1 is equal to sigma wj. Advantages: automatic feature selection and interpretable models. Classification algorithms. Classification predicts discrete class labels, and it's based on probability. So let's say if the probability, let's say, is greater than or equal to 0.5, the answer is considered yes. Otherwise, it's considered no. This is how it works. By the way, this is how the perceptron in neural networks work. This is how it's activated. If you cross a threshold above 0.5 or equal to 0.5, it fires out, okay? Based on the function that's actually in the perceptron, which is one neuron within the neural network. Otherwise, it doesn't fire. And you would have multiple inputs into that perceptron, not only one. In other words, it's not only one feature, plus it's not only one meshing, because you would have the input stage, you have the middle stage, which is the hidden layers. This is where the processing happens, and the output layers, this is the one that decides, okay, this is blue, black, this is yes or no. The logistic regression models class probability using the sigmoid function. Okay, sigmoid function is given by 1 over 1 plus e minus z. This is called the sigmoid, and its drawing is like that. I think, if I'm not mistaken, something like that. You have also the hyperbolic tangent. Yeah, it works something like that. So when you cross a specific threshold, the answer is considered 1, or the neuron would be activated, so to speak. The function is z equal transpose of w times x plus b. B is the bias, and w is the weight matrix. Now, probability of class 1 is given by py equal 1, for example, and this would be the class. 1 would be, for example, yes or true, and 0 would be no or false. These are the labels. So probability of y equal 1, which means the answer is correct, is given by 1 divided by 1 plus e minus e exponential to the power of minus z. So the decision rule would give you true. Okay, so the neuron would be activated if probability is greater than or equal to 0.5, or the 0, which means that it wouldn't be activated otherwise. Loss function binary cross entropy. At first, what is entropy? What does it mean? Entropy is actually the amount of data necessary in order to represent an information. So the entropy for a prediction or an actual outcome is given by 1 over n, which is the number of samples, multiplied by sigma, which is the sum of, for each outcome, okay, the value for that outcome multiplied by the logarithm of the probability for that outcome. I think it was Claude Shannon's law for entropy. Okay, it was, or Nyquist, yeah, law of Nyquist. That's in the theory of information. So here, binary cross entropy, meaning the cross entropy between the actual value, okay, the probability for that value being true of occurring, plus 1 minus yi, which would be actually, yeah, 1 minus the value multiplied by 1 minus the probability, log 1 of 1 minus the probability of it happening. In other words, that would be log of the probability of not occurring. Okay, so the differential between the two is called binary cross entropy, given by minus 1 over n, total number of samples, multiplied by sigma of I equal 1 to n, total number of samples again, yi log pi, pi being the probability of yi outcome, plus 1 minus yi, which is anything but that value. So it is the difference between that value and 1. It's the opposite for that value, multiplied by log of 1 minus pi, which is, in other words, saying log of the probability of that value not occurring. This is called the binary cross entropy, which is a loss function. It is used to determine the amount of loss for that prediction, how much deviation you have from the truth, okay, from the accuracy. K and n, or K nearest neighbors. K and n is a non-parametric algorithm based on distance similarity. Distance metric, which is an Euclidean distance simply, is given by, okay, if you have the distance between two values in one dimension, or 2 points in one dimension, okay? So the value for the first point is x1, value for the second point would be x2. What would be the distance? It would be the square root of x1 minus x2, I'm sorry, x1, yeah, correct, x1 minus x2 square. But when you have multiple dimensions, what are the dimensions? They are simply the features. So having multiple features, for each feature, you would need to do the same thing, measuring the distance, which is square root of x1 minus x2 square, and you need to add that up. So it would be square root of x1 minus x2 square plus z1 minus z2 square plus t1 minus t2 square. Actually, here the index would be different. So yeah, x1 minus x1 1 square minus x1 2 square, etc. Now, prediction obtained from majority vote. So that would be based on measuring the distance between different points. So how close is this value from first category in respect of the second category? It would determine whether it belongs to the first or the second category. Characteristics, and I will explain it further in a moment. Characteristics, no explicit training phase. You don't need a training iteration or a set of iterations, and it is sensitive to feature scaling. So if you scale, you might mess the entire thing up. Now, to give an example on how it actually works, let's say we have here a set of values. Actually, you have at first x and y axis, with x having the length of fur for, let's consider two types of animals here, cats and dogs. So x would be the length of the fur that it has in millimeters, and y would be the thickness of that fur. Now, let's suppose that when the fur is tall and thick, you would have a dog. So we are trying to detect the type of the animal based on that feature. Actually, these two features, because we have two in this case. You might have more. So for a thicker and longer fur type, you would have a dog, and a dog is represented by X. So you would have all the dogs on the database or data set being here almost, okay? Now, some of the values might also intertwine, like they might invade the area which is supposedly belonging to cats, okay? Because you have multiple types of dogs and cats. Meanwhile, the cats that are represented in rounded shapes, okay, circles, these are, okay, the cats predicted, not actually, like this is the cats data set from the data set that usually have smaller or shorter fur with a thinner thickness, okay? Now, let's say for a new specimen that I measured, I got this value for like this thickness for the fur and this length for the fur, okay? So the new value is here, and I'm trying to predict whether it's a dog or a cat based on this measurement of both the thickness of the fur and the length. So this is how it works. I need to get to the closest neighbors to measure the distance from that point to the closest neighbors, whatever these neighbors are. So here, the closest neighbor is this one. The distance here is 2, okay? This is the closest so far. Then the second closest neighbor is this, okay? Distance is 2 also. So the closest neighbor is this. Distance is 2, okay? Then you go further depending on how much resolution you want to have. So now let's consider only these 4 closest neighbors, k nearest neighbors. This is why it's called KNN. So among these neighbors, you have 3 among these closest neighbors are dogs, and the 4th happens to be a cat. So it's 3 dogs, and the 4th closest happens to be a cat. So based on the majority vote, since the closest ones, like the highest number of the closest neighbors happens to be dogs, so you can predict, or you can actually give the outcome as being at this specimen being actually a dog. Of course, there's a margin of error, okay? But based on the majority vote, and it can give you a high accuracy, by the way, in some scenarios, you have the best estimation of that new species being a dog, not a cat, okay? Because 3 of or among the closest neighbors are dogs, not cats. This is how it actually works. Of course, when you have multiple, like more than 2 features, the distance would be, again, this is an Euclidean distance. So just as we measure the distance from here to here, it is the square root of x1 minus x2 squared plus y1 minus y2 squared. Just like the distance between 2 points in space, it would be square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. When you have multiple dimensions, you keep adding them up. This is how you get the distance. The shortest distances, you get the closest of these neighbors, and this is how you assess, okay, what is the majority? If it's dogs, then it would be a dog. Here in this representation, or in this illustration, so k, which is the number of neighbors to be considered. Again, when you increase the number of neighbors, it can increase accuracy. It can at times degrade it, okay? But here, the number of neighbors taken in consideration is 3. So you see that the closest neighbors are actually the blue category instead of the red, because you have among the 3, 2 that are the closest, and the third one is red. So based on a majority vote, this category, like the category or the class of this dot, is blue. Doesn't matter what blue actually means, okay? But based on proximity here, the majority of these, based on the vote majority, okay, the majority of the closest points to the green one is blue, so this one is blue. Another type of algorithms is the decision trees. Decision trees recursively partition feature space. A split is selected by minimizing impurity. You have the concept of entropy again, which is sigma probability multiplied by log 2 probability of the value of occurrence. Information gain Ig is given by Hs, which is the entropy minus sigma of the ratio between Sk and S, multiplied by HSK. Alternative impurity measures Gini index, which is 1 minus sigma Pc squared for C. Random forests. Random forests combine multiple decision trees using ensemble learning. So the prediction would be equal to 1 over t, where t is the number of trees multiplied by the sum of the function, okay, that actually deriving the prediction from the tree. Ft, okay, is the function, prediction function for the feature. Now, key concepts are the bootstrap sampling, feature randomness, so you'd have a random releve or random extraction of values, and variance. The main purpose would be variance reduction also. So you'd have different trees, and from these trees you are getting the average value, so to speak, the average prediction from these trees to come up with the final prediction. Now again, to give you an insight into what a decision tree would look like, and a random forest again is a combination of multiple decision trees. So you'd have, for example, here color equal red. Okay, if color equal red, if the answer is yes, you would go to one strand of the tree. Otherwise, you would go to another strand. Now, if it's red, if the model is greater than 2010, for example, that would be concerning a car. So if it's greater than 2010, then you buy. Okay, that would be a decision tree. That's why it's called decision tree. Otherwise, if the mileage, so otherwise you'd go to another condition. If the mileage is less than 50,000 kilometers, then you don't buy. Otherwise, you would buy. Okay, so you go for each point, for each condition, there's yes or a no, and it sends you into different decision trees, subtrees. That would be altogether a forest. Okay, so based on each point value, you would go in one direction or the other, where you would be met by other different conditions that would send you. So it's like a recursive tree processing, okay, a recursive traveling within a tree of decision in order to obtain the final outcome. SVM, or support vector machines. SVM finds the optimal separating hyperplane. So it is given by the equation, which is a linear equation, WT, or the transpose of the weight times x plus b, which is the bias, is equal to 0. Where you have the hyperplane vectors, these are the two vectors separating the two classifications, the two classes. Class A being the red category, whatever that is, and the blue would be another category, class B, for example. So these vectors would separate between the two so as to being able to predict, okay, when you have a value that's an outlier between both, of course, if it's a value that is within this domain above the other support vector, which is in the red zone, or below the other one, okay, which is in the blue zone. So if it's in either places, it would be easily predicted as being red or blue respectively. But if it's an outlier, so to speak, between these two vectors, it should be approximated based on the margin, how close it is from one or the other. This is how it's estimated. Of course, there's an error margin both ways. Now, margin maximization, optimization problem. So the margin is given by minimum of 1/2 w squared, which is the distance, so to speak, okay, subject to yi, the predicted value, wt xi plus b is greater than or equal to 1. Soft margin with slack variables, so minimum of 1/2 w squared in order to minimize the error margin, plus c sigma key I. Okay, kernel trick enables nonlinear classification. Kxi xj is equal phi xit phi xj. Common kernels are linear kernel, polynomial kernel, that would be a polynomial curve, and RBF or radial basis function. Kxi xj is equal to exponential minus gamma xi minus xj, distance between two, squared. Finally, as a summary, supervised learning algorithms learn mappings from labeled data that are predefined, so we know what to expect at the end, in order to perform prediction tasks. Regression methods estimate continuous outputs, while classification algorithms assign discrete labels. So continuous values would be a number, a value, okay, like for example, the power, electrical power, or the intensity of sound, that would be a continuous value. However, when we're talking about classification algorithms, okay, these are meant to classify an outcome as being a discrete value, a specified fixed value, such as dog, cat, such as true, false. These are the discrete values that we are talking about. Regularization, distance metrics, such as KNN, such as SVM, tree-based learning, such as the forest or the decision tree, okay, binary forest or like a random forest, and margin optimization, such as SVM. Form, actually, yeah, the margin is SVM algorithm, not the KNN. There's a difference here. Okay, form the mathematical foundation of modern supervised machine learning systems. Module 3, Model Evaluation and Performance Metrics. Model evaluation quantifies how well a machine learning model performs on unseen data, which means new input, new data, how accurate it is with handling new data, which is not a part of the data set that has already been learned. Performance metrics guide model selection, which means which model, which algorithm would be better for a specific scenario, such as SVM or whether it's KNN in classification algorithms. Hyperparameter or naive Bayes, by the way, which is probability-based model. Hyperparameter tuning and comparison between algorithms is part also of the evaluation and performance. Okay, so it's based on tuning and comparison between algorithms to select the best one, the one most fitting for the scenario in hand. Evaluation differs depending on whether the task is regression or classification. So if it's regression, it would be dealing with continuous values. If it's classification, it would be dealing with discrete labels, discrete values. Given a data set D equal xi, yi, where x is the feature, y is the prediction from I equal 1 to n, where yi represents true labels and yi hat denotes the model predictions. So yi hat is the prediction of the model. Performance metrics measure prediction error. So how much gap there is between a predicted value and the actual value. Actual value being yi, that's the true value for a sample, and the predicted value is the one that has been outputted by the model, which is denoted by yi hat. Performance metrics measure prediction error or classification quality. Regression metrics evaluate prediction accuracy for continuous valued outputs, which means a prediction model that outputs a continuous value, such as the power level or the temperature predicted. That would be a continuous value, not a discrete value, not like based on a finite number of results, such as yes or no, true or false, red, green, blue. These are finite values, discrete values, and not continuous. When we talk about continuous values, that would be like the parameters, physical parameters in the universe, such as you have temperature, pressure, etc. Let's start with the mean squared error or MSE. The mean squared error or MSE measures the average squared difference. So it's squared in order to increase the gap. It's like zooming into the error gap so as to be bloated in order to make it more distinctive. The difference between the predicted value, y hat, and the actual value. So the mean squared error measures the average squared difference between predicted and actual values based on the following formula. MSE is equal to 1 over n, n being the number of samples, total number of samples, sigma I equal 1 to n of yi, which is the real actual value, minus yi hat square. So it is not only just the gap, it is the gap or the distance between these two values squared. Again, it's like placing the magnified glass on the chart or like the illustration presenting the actual values and the predicted values in order to enlarge the difference, to make the difference between current value and predicted value more explicit, more prominent, so as to be able to distinguish better how much error margin do we have. Properties penalizes large error strongly. Here's another advantage. So the large errors that you would have between one point, okay, one predicted, actually between the real point and the point that is predicted based on whatever algorithm you have, that gap increases like parabolically, okay? So it's squared. So it's like an exponential increase, not exponential, but parabolic, so as to increase and penalize large errors dramatically, okay? This is the advantage. Second, differentiable, which what we were talking about, suitable for gradient-based optimization. So it can be distinguished when you have a gap, even if it's a small gap between current value and predicted value, because in this way, you are bloating it up in order to make that gap more pronounced so that you can gain more accuracy and a better optimization. And it's more sensitive to outliers. Why? Because outlier values would be like the values that are much further from the curve. So squaring them up would even push them much further. RMSE or root mean squared error. RMSE is the square root of the MSE, as simple as that. It's given by square root of 1 over n, sigma I equal 1 to n, yi minus y hat I square. The advantages are the same unit as target variable, okay? So it's like same unit value as the target value, target variable. and it would have an easier interpretation compared to MSE because the MSE is more of a bigger gap, okay, being produced by it between the current or actual value and the predicted value. So instead of having this bigger gap, you are more going through or like into a direction of normalization and a lesser stretching between the current value and the slope of prediction. If it's a slope, if it's a nonlinear equation, that would be a nonlinear curve. Okay, so it's more confined, more constrained, like more tied up, more tightened than the MSE. So again, the advantages, same unit as target variable, easier interpretation compared to MSE. Mean absolute error, or MAE. MAE measures the average magnitude of prediction errors, which is simply for each value of a feature, you measure the distance between that value, the real value, okay, and the predicted one. So for each value for a feature, you measure the distance between the correct versus the one that is predicted by the prediction model or algorithm. You add them all up, then you divide them by the total number of samples, which is n. So MAE is equal to 1 divided by n. Sigma I equal 1 to n, which is from the first value all the way to the total number of values. Yi, which is the real value, minus yi hat, or the predicted value, in absolute, which means that we want them to be positive numbers. The difference, we want it to be positive, not negative. Characteristics, less sensitive to outliers than MSE. So outliers would be more tolerable compared to the mean squared error because you're not elevating to the square, okay, the difference for each parameter, for each value being measured, and it produces sparse gradients. So the gradients would be more sparse. Another note here concerning what does sparse gradients mean. It means that the values would be more dispersed, okay? They wouldn't be in one location. So they would be more scattered, better to work with, not focused in one area. R-square score, coefficient of determination. This is another metric which evaluates how much variance or variance in the target variable is explained by the model. R square is equal to 1 minus sigma I equal 1 to n, yi minus y hat I square. Again, y is the real value, y hat is the predicted value, divided by sigma I equal 1 to n, yi minus y mod y in bar square, which is the mean, okay? That's the average. So where y bar or y bar is the mean of observed values, interpretation. Now, for r squared is equal to 1, that would be a perfect prediction. R squared equal to 0, model equals mean predictor, so the model is equal to the mean predictor. And for r squared less than 0, it would be worse than baseline. The prediction would be of a lesser quality, worse than the baseline prediction. Classification metrics. Classification metrics evaluate performance when predicting discrete categories, which means the categories of prediction that give us discrete results, such as false, true, such as yes or no, negative, positive. For example, let's consider we are testing for a disease, the presence of a disease. We have 4 symbols here. We can denote it by 4 notations, so to speak. You have TP or true positive, which means that the individual has been tested for a disease and actually he is plagued, like he has the disease on the inside of him. So it's positive, he tested positive, and he's actually positive. He actually has the virus or the infection. TN or true negative means that the individual has tested negative and is actually negative. He doesn't have the virus. FP, false positive, So he tested positive, but he's negative. He doesn't have the flu or like whatever. And Fn, which means false negative. So he tested negative, but it appears that he is positive. The test came out negative, but it's not true because the person carries the virus or the plague within them. Let's get into the metrics. Okay, accuracy. What is accuracy? It measures the overall correct predictions or the rate of prediction correctness in respect or like compared to the total number of predictions. So the accuracy is given by the correct predictions, which is TP plus Tn or true positive plus true negatives, divided by the total number of predictions, which is TP plus Tn, true positive, true negative, plus false positive plus false negative. Limitation, misleading for imbalanced data sets. It is misleading when you have an imbalanced data set. So why is that? Because you would have the number of true positive and true negatives. Okay, like you have, number of true positives way bigger than the number of true negatives. So you don't have balance. Okay, it's not balance between positive and negative. You would have more negatives than positives or vice versa. Okay? So, precision and recall. Precision. The precision measures correctness of positive predictions. Okay? So how much the positive predictions are correct. Which means precision is equal to true positive, the correct positive values, divided by the total positive values. So divided by true positive plus false positive. So all the positives, whether true or false, how much is there true positives among them, which have tested to be true, and they are actually, which have tested to be positive and are actually positive. High precision implies low false alarm rate. Okay? Another metric is recall or sensitivity. Recall measures ability to detect actual positives. So it is given by true positive divided by true positive plus false negative. So, okay, it's a little bit hard to explain, to break down, but you can memorize it as being the true positive divided by true positive plus false negative, which is the ability to detect the actual positives. High recall implies fewer missed detections. Okay? So in other words, when you have a high recall, this is when you can admit that you have fewer missed detections. What are missed detections, by the way? The false negatives are actually positives that you have missed through the test. This is what it means. Okay? So it is the true positive divided by the true positives that have been detected and the false negatives that are actually positives that did not come out in your test. This is the metric, okay? Because the false negatives are actually positives that went undetected. So a higher recall, it implies fewer misdetections. So the detection rate is much higher. F1 score balances precision and recall using harmonic mean, which is 2 multiplied by precision times recall divided by precision plus recall. Useful when class distribution is uneven. Confusion matrix. A confusion matrix summarizes prediction outcomes. So you have true negative, false positive, true positive. This confusion matrix, it summarizes the different detections, which one is true positive, which one is false positive, okay? And which one was true or false negative within a matrix form. It provides detailed insight into the classification errors and also the performance of the model. Okay, the class-wise performance, in other words. ROC curve and AUC, okay, which is receiver operating characteristic curve. Okay, you have the true positive rate TPR is given by true positive divided by true positive plus false negative, okay, which was the recall also, false positive rate, FPR, which is false positive divided by false positive plus true negative. Okay, so false positive is actually, these are not positive actually. In reality, they are negative, but they have been assessed mistakenly as positive. So FP divided by false positive plus true negative, these are the real negatives, okay? ROC, or receiver operating characteristic curve, plots TPR versus FPR for different classification thresholds. AUC, or area under the curve, as you know that the area under a curve from x equals 0 to x equals 3, for example, for any function, is actually the integral from 0 to 3, or between 0 to 3, of the function. This is how you get the area under that curve. So AUC is given by integral between 0 and 1, TPR, true positive rate, multiplied by false positive rate, times DFPR. The differential is the false positive rate. Okay, so interpretation. If AUC is equal to 1, that would be a perfect classifier. Okay, so the true positive rate is 1. It's like absolute, right? Now, if AUC is equal to 0.5, you have a random guessing going on. Overfitting versus underfitting. Model generalization depends on balancing complexity, the complexity of the algorithm, and the learning capacity, how much it can learn, versus the complexity. Okay, when it's over-complexed, which means when it's perfectly fitting all the current values, okay, it would be hard for the model to learn new values, okay? Meanwhile, if it's oversimplified, it would have like, it can be, okay, to some degree, more general, except that the training error, okay, the error would be much larger, and I'm about to explain it a little bit further. Let's go at first into underfitting, and then I will draw the difference. So underfitting. When do we have an underfitting? It is when the model is too simple. Give you an example. When you have a linear prediction, okay, linear regression predictor, when the values are not scattered linearly at all, they might be following a nonlinear pattern. So a linear predictor would incur a much larger number of errors. Okay, so it would be highly biased. So the gap between the actual correct values and the predicted values would be much larger. Okay, and low variance, so the variability would be much lower. Okay, so this would cause us to have a high training error and a high test error. So the test would appear to have much larger number of errors. Okay, so the accuracy would be very low, and it wouldn't generalize well. Generalization means said for new values, okay, you would have a high, actually in both cases it wouldn't generalize well, both an underfitting and overfitting. Why? Because for new values that you are giving the system, you would have a large gap of errors. So to actually give you an example of underfitting, okay, so let's say you have here different values, okay, this would be, yeah, like the scale. Okay, so here you have a different number of values, and if it appears to you that they are linear, they are actually not. Notice, okay, they are not linear. So if we try to predict these values by this simple line, that would be an underfitting. Why? Because yes, the model is very simple, except it would have a much larger number of errors, because you see these values, all of these values here seem to be much further from the linear regression line. Okay, So they appear to be outliers. Okay, so in this case, there would be a high training error, okay, and a high test error. So the errors for the testing would be much larger because as you see here, the values seem to be much further from the line. The correct thing to do is to actually have a line. Okay, let me try at first. Let me get this color. Okay, so the actual more correct value would be a curve like this one. Okay, I'm trying to draw it in a much better, yeah, it would be something like that. Okay, something like that. Okay, it's like a fraction of a sine wave, so to speak. So that would be more fitting. Okay, it would be closer to the values that seem to be outliers, because the representation itself seems to be a nonlinear representation of the values, much further than a linear regression plot. Overfitting, it occurs when a model memorizes the training data to the point that it can no longer predict accurately based on a new input. So it has been almost perfectly adapted to the already ingested data, the already ingested input in the data set. So when it has new values being pushed into the system, into this algorithm or model, the accuracy comes out degraded. It would have a high error due to the fact that the curve has memorized perfectly the already ingested data, but any new data, any new input would be much further. It would be with a wider, larger gap than the actual value, correct value that is predicted to be obtained in such case. Okay, so the labels would be far off than like the actual value at the output. So in such case, you would have low bias, which means that the curve is overly fitting and so adapted to the already existing values in the system, and high variance. Okay, variance or variability, which means that the curve is so complex, so changing based on the inputs that it no longer has degrees of freedom that are enough for it to predict new values. Okay, so characteristics: low training error, which means it has been trained well, except that it has been trained well on the already existing input, that for a new input it would not perform well. It would have a high validation error and a high test error. So values that are not among the training set would give you a much further divergence. Okay, they would be far off from the real labels, the real values. Okay, so the predicted outputs would be much further off the real outputs, incurring more validation and test errors. To give an example here, so let's say this is, yeah, actually I'm gonna use the red at first. So you have, let's say, a set of values that are something like that. Okay, it's like an exponential distribution, so to speak. Okay, and you have like, yeah, this distribution, but you have too much scattering up and down. So what is overfitting? Overfitting would be like this. Okay, so you see the curve, it's almost following a lot of different values, to the point that here, when you have a specific outlier, so to speak, or like a value that needs to be predicted that is outside of the range, okay, the gap between that value, and you see how complex it is, like the equation would be much complex, more complex. So the gap between the real value and the predicted value would be like a further gap, a longer gap, a higher error margin, in all different values that need to be predicted. Okay, so that would be an overfitting, incurring high validation and test errors. Now, as a comparison, or like the perfect slope in such case, so to speak, which is less complex, a more less overfitting, fitting but not overfitting, would be something like that. Okay, that would be like an exponent, and here it turns like a cap. Okay, straightforward line with less curvatures. Okay, it would be more simple. By the way, a simpler curve would mean lesser iterations in processing, less processing power needed in order to produce the outcomes or the results, with also high validation accuracy and test accuracy and low margin of errors. Bias variance trade-off. Expected prediction error decomposes as E of y, which is actually the correct value, the correct outcome, minus the predicted outcome, y hat, or fx hat is actually y hat, which is the predicted value or the prediction function here in general, square is equal to bias square. So error, prediction error is given by bias square plus variance plus sigma square, where the bias measures actually the systematic error. Okay, how much error, how much gap there is between the real value and the predicted value. Variance measures sensitivity to training data. In other words, this is the variance. How much the curve is sensitive to the training data. How much, in other words, the variance is how much is the prediction curve, okay, far away from the actual training data. So let's say, for instance, you have these are different values in the data set. Okay, these are the learned values, and that would be, let's say, the prediction curve. Okay, so how far is the prediction curve from the actual values that are being learned by the system? That would be the variance. So if you have too much variance, you would have something like this curve here. Okay, I didn't change the color. It would be something like this curve. Okay, you notice how far is this curve from the real values. So that would give you a high variance. It's less sensitive to the actual learning dataset values. Plus sigma square. Sigma square is the irreducible noise of prediction. The goal is to minimize total generalization error by balancing the bias and variance. Okay, so with more bias, you would have more error, so to speak. With variance, I think variance might be actually denoting here the opposite. Like, actually, variance is the variability. How much is there, or how much distance is there between the prediction curve and the real values, how they are distributed on this scalar. Finally, model evaluation provides quantitative tools for comparing learning algorithms. Regression metrics measure prediction error magnitude, while classification metrics analyze decision quality, such as accuracy, precision, all of that, and probability discrimination. Understanding overfitting. Underfitting, as a reminder, is when you have, for example, a linear regression. You're trying to fit actually for a nonlinear pattern of distribution for the values to be learned for your prediction model. So it would have a large gap of test errors. Why? Because the linear regression is like this. Meanwhile, the distributed scattered values are like that. They are much further than the linear model, okay, and they are distributed non-linearly, so it would be much lesser accurate, okay, much less accurate. Now, understanding overfitting, underfitting, and the bias variance trade-off is essential for building models that generalize reliably, that you can rely on, to real-world data. Module 4, Unsupervised Learning. Now, unsupervised learning involves discovering hidden structures or patterns in data without labeled outputs, which means that you don't have label for them. You don't know what these predictions actually are, but the system, the model, is able, based on the differences between the different values, to classify them into different categories, okay, that have not been pre-designated, but these are different categories to be generated based on the differences, based on, like, so to speak, the divergence between these values, okay? So whether they are scattered based on amplitude or frequency or whatever, depending on what type of feature you have, these different points would be classified into different categories. Just like when you have different colored balls, you would classify them, for example, based on the frequency of the color, because each light wave, each color is actually a different frequency. Okay, now given a data set, d is equal xi from I equal 1 to n, xi is within R, the real numbers, in a dimension d. The objective is to learn intrinsic organization, such as clusters, different categories, low-dimensional representations, or associations among variables. Unsupervised learning is widely used for exploratory data. Okay, exploratory data analysis, for which we don't actually have a designation for the categories. We're simply trying to explore different categories that might exist, or different classes, or different labels that have not been predefined. So it is used for exploratory data analysis, feature learning, learning the features, anomaly detection, which means detecting something that is an outlier among different values, and recommendation systems, so it recommends something based on, like, you've been requesting a specific type of program on the internet, okay? So that model is actually similar to other types, although we had not designated or like defined the type yet, except that these different values are so compatible or matching the value or the category that you've been ordering. So these belong to the same class, and hence that would prompt, for example, any decision algorithm in such case, which is working on the unsupervised learning models, to suggest to you or recommend a program based on that same category. Clustering. Now, clustering partitions data into groups such as samples within the same cluster are more similar to each other than to those that are outside the cluster or that belong to other clusters. This is how clustering works. So, gathering the data points that have too many similarities, that are matching. This is how we classify different values based on, or different inputs based on similar values. Okay, these would be considered as similar category, okay, as belonging to the same category. K-means clustering. K-means divides data into K clusters, okay, by minimizing within cluster variance. So you would divide data into K clusters, K number of clusters, and this is how we minimize within cluster variance. We minimize the variance within the cluster, okay, and this would be divided into K clusters. Objective function. J is equal to sigma, K equal 1 to K, sigma xi within ck within the cluster, so xi is within the cluster range or size of xi minus mu k squared. So this is the modulo, the distance of the vector square. What is the vector distance? Which is xi minus mu k. Okay, so let's say xi has xyz, okay, and mu k is the centroid. This is another point, which is the mean value point, by the way, also has xyz. So the distance between them would be given by the square root of x minus mu x squared, okay, x of the point, okay, xx minus mu x squared plus xy minus mu y squared, just like the distance between 2 points. Here, that would be the vector distance plus xz minus mu z, mu kz, of course. Of course, you have a k also. The k is the index, or it's a denoter that it is the centroid. So it's actually called mu k. So mu kx, mu ky, and mu kz, okay? K, k, and k. Square, that would give us the distance, and you square it after that. All right, now mu k is actually the centroid. What does the centroid means? It means that it is the point that has the mean value of coordinates, okay? That would be given by 1 divided by c, which is the number of the points within the cluster, or the cluster size, okay? Times, it's like an average point, by the way. It is an average point, or a mean point, times x sigma xi, which is x1 plus x2. So all the x's, all the values within this cluster, you add them and you divide them by the size of the cluster, or the number of points or samples if you want. Okay, so this is mu k. It is actually a point. So it's not, yeah, it's an average point, but it's still a point. Why? Because you have, let's say it is 3 coordinates, so to speak. Although here we're talking about one feature. If it's 3 coordinates, so for y also 1 over ck times y1 plus y2 plus y3, etc. For z, 1 over ck times z1, z2, z3, depending on the number of features. Okay, so this is how you get actually to define different clusters or different categories. Now, to give you an example, let's say you have here different points. Okay, and here you have another category. Let us draw them in blue. Okay, so what would be the cluster? Okay, consider these as points, not dashes. Okay, just for the sake of convenience, they are being produced as dashes. Okay, so let's say this is the centroid here. Okay, so the centroid is mu k. What would be the cluster? Okay, what would be the points belonging to the cluster? They would be these different distances of different points to the centroid, okay, which is given by xi minus mu k square, okay, sigma sigma. Algorithm steps. Okay, how does it work? First, you initialize k centroids randomly, so they are picked up randomly, okay? They are not like pre-designated or something. Then assign each point to the nearest centroid. So ck is equal to argmin, or minimum distance between xi and mu k, which is the centroid that has been chosen, okay, randomly. Then we keep updating the centroids, okay, so the centroid would change, repeat until convergence, until we have the point where you have for different other points, or like we repeat until the centroid that has been chosen has all the surrounding points being placed at the minimum distance to that point, okay? So k-means assumes spherical clusters and requires predefined k. Hierarchical clustering. This type of clustering builds a tree structure, dendrogram, representing nested clusters within it. Okay? Now, the distance between clusters, that would be called the common linkage area. If you have single linkage, so DAB between cluster A and B is given by minimum distance between X minus Y. Complete linkage, so complete linkage between these two clusters would be the maximum distance X and Y. Or in other words, that would be the maximum distance between like the further value that's on the edge of the first cluster and the opposite value, which is the further or the furthest on the other edge, the farthest on the other edge. That would be the maximum linkage distance, okay? Maximum for the complete linkage. For the single linkage, that would be the minimum distance between the closest values belonging to both of the clusters. So the closest ones, that would be the minimum value, okay? The minimum distance for the two closest variables or values within the two clusters that are at proximity. Average linkage. Okay, so at first, we've seen so far the single linkage and the complete linkage. The first measuring the minimum distance between any two values, the first belonging to the first cluster, which is A, second belonging to the second cluster, which is B. So, if we measure the distance between any 2 points, the first belonging to the first cluster, the second point belonging to the B cluster or the second cluster, what would be the minimum distance that you can get? That is the single linkage, all right, which is the minimum X minus Y distance, all right? Now, the complete linkage, which was the second metric in the previous slide, is actually the maximum distance. So, it is the distance from the point at the edge of the first cluster, which is the farthest point, and to the point of the second cluster, cluster B, which is also at the farthest edge from the B side. So max X minus Y, this would give us actually the complete linkage. Now, for the average linkage, DAB is given by 1 divided by A times V, which is all the number of segments that you would have between the first cluster and the second cluster. I will give a more explanatory way for that, a more explicit way to pinpoint that, what is 1 over A, B. Sigma X belonging to A cluster, B belonging to B cluster, X minus Y. So X minus Y1, Y2, Y3, the distance, so measuring the distance between X, okay, the first value of the first cluster and all the other values of the B cluster. Then you go to the second value of the A cluster, also you measure the distance between that and all the other values of the B cluster, etc. Then you divide it by all the segments that you can get. This would give us the average linkage. I hope it's clear. Now you have two approaches, agglomerative, which is bottom up, and divisive, which is top down. Now to give you a clearer way, so let's say we have, okay, these are the X's of the first cluster, and this is the Y cluster here. Yeah, we will note them by the Y letter, okay? These are different values for the B cluster, I'm sorry. So we have B cluster, A cluster. So the minimum distance seems to be for me like this one is the minimum distance, which is, that would be the single linkage, okay? Single linkage distance. Now, the complete linkage would be the distance from or between the further, like the farthest points of A and B. That would be that distance from X and all the way to y. Okay, located at both edges. Now, 1 over AB, okay, so how many linkages you would have between A and B? So you have x to y1, x to y2, x to y3, to y4, to y5, okay? So that would be the number, in other words, okay, between each point here, how many linkages you had to have with the other points in cluster B. It is simply, these are the total number, this is the total number of linkages that you can get. It is 1 divided by the size of cluster A, which is in this case 1, 2, 3, 4, 5, multiplied by the size of cluster B, 1, 2, 3, 4, 5. So you have 25 total linkages, okay? 1 over 25 would be the number, total number of linkages, okay? 1 divided by total number of linkages. And this is how you get the average. Average is another word to say the mean, okay? Multiplied by x minus y, so distance between x, y here, then plus distance between x and the other y, then x and the third y, etc. for all the points. So after we're done with that, x1 minus y1, distance meaning square root of x minus y squared, okay, plus x1 minus y2, the distance squared, etc. all the way, okay? Great. So you keep measuring all distances, you divide them by the total number of stretches or distances, which is 25, and this is how you get the average linkage. DBSCAN, or density-based spatial clustering. Now, DBSCAN, and of course here we highlight the two words density-based, or density alone is sufficient. So unlike the former algorithm, which was the k-means, that works or classifies different categories based on the distance from a centroid to be designated and updated, the DBSCAN identifies clusters based on the density or the number of values at a proximity of a specific point or within a certain radius. Okay? Now, it is based on density rather than distance. Again, the parameters would be epsilon, which is the neighborhood radius. So, how far is the radius, which is the distance between the center and the outer edge point, and the minimum points, or min PTS, which is the minimum number of points required to be existing within that dense region, okay, for them to be classified as belonging to the same category. So the neighborhood definition, n epsilon xi is equal to xj, given that xj minus xi in modulus, this means the distance between xj at the index x of index j, okay, a specific value point, and the central distance, the central position, should be less than or equal to the radius. Points are classified as core points, which would be the points that are the closest to the center, border points, which are at the border, or in other words, they would be with at a distance that is equal actually to epsilon from the center, and noise outliers. So these would be outliers that are a little bit outside of the radius, okay? So they can be considered outside of the category, except they seem to have been, or to should have been designated a part of that same class, except they did not fit the criteria of having a distance of a maximum of epsilon from the center. Advantages: detects arbitrary shaped clusters and automatically identifies outliers. So it can detect the clusters that are close to each other that are arbitrarily shaped and rounded. Now, to give you a picture at how it would look like, so let's say you have here this would be the center, xj. Then for each point xi meaning x1, x2, x3, x4, etc. Okay? Now, let's say that epsilon, okay, this is x6 or 7, whatever. So let's say this is the radius here, okay? Actually, it's not an exact radius. It seems an ellipsoid, but you get the point. It should be rounded, okay? So any point outside of that radius is not considered to be part of the same category. What are the values that fit the premise or the condition, okay, that actually make the fitting, make the mold? These are x3 here and x6, okay? x6? I don't think this was x6. Yeah, anyway, I don't know. x4, I think. This was x4 or x2 or whatever, okay? Let's say it was x2, okay? So these two values have a distance, which is modulo of xj minus xi, less than or equal to epsilon, okay? Why? Because epsilon is the radius. So if you have a point which is right at the radius, it's still part of the same category. But outside of that, all of the values would be outliers, would be outside of this class. Again, as a reminder, how do you measure the distance between xj, which is the center here, and let's say x1? If we consider it to be a unidimensional value, okay, it's one feature, in other words. We're not measuring based on other features. So that would be the square root of xj minus x1, in this case, square. Or in other words, it can be written as it is written here, xj modulo of xj minus x1. And of course, the premise or the condition, it should be less than or equal to epsilon, which is the maximum radius of this cluster, to be designated as a point belonging to this category or cluster. Dimensionality reduction. This is something that we need to do when we have a problem, we're facing like a struggle or a dilemma, such as having very, very low values versus very high values within the set. This is usually encountered in scenarios when you have astronomical values, or you are collecting signals of light from an astronomical object in order to measure its size, its radius, for example. So you might be dealing, and this also can apply to like sensing the intensity of light being received or the intensity of sound. So you might be dealing between minus 60,000 milliwatt up to tens of thousands or hundreds of thousands or billions milliwatts. Okay, so the scalar won't work because you have a very large magnitude of value. You have a big gap between low and high values. Okay, so we need to reduce the dimensions. One of the ways is applying or using a logarithm that has a low rate of increase, even when the x-axis is increasing at a high rate. So it has a slow slope, although it grows up to infinity, but it grows very slowly. That would be a clever way in order to deal with such a problem. Okay, while improving, or like we improve that while preserving important structure, which is the difference gaps between different values. Now the PCA, or principal component analysis, finds orthogonal directions between values to maximize variance, to maximize the gap between different values. Now going back to dimensionality reduction. So you would have something like, yeah, let's say I'm working with the logarithm, okay? So you notice you have 1, you might have 10, you might have 100, 1000, 1 million, let's say 10 to the power of 6, okay? So the logarithm, let's say we're talking about log base 10, it would have a very slow curvature of increase, okay? I don't know exactly how, I don't remember exactly how it increases, okay? So yeah, you have ln1 is equal to 0, ln10 would be 1, ln100 would be 2. Okay, so notice something. When you have 10 to the power of n, let's say 10 to the power of 6 or million, you would have a value of a colossal astronomical magnitude. But when working with a logarithm, the value in logarithm of that 10 to the power of 6 would be 6, would be the power or the exponent of the value instead of the value itself, which can reduce enormously the value, the scale of the values that are being measured. So let's say, again, for log base 10 of 10 would be equal to 1, okay? So log base 10 again of 100 gives us 2. Log base 10 of 1000 gives us 3, etc. And log base 10 of 10 to the power of 6 gives us 6. So you see, you notice how much minimum the values have become. Now, if we're dealing with negative values, so if you have, let's say, 10 to the power of minus 3, okay, 10 to the power of minus 3, so log base 10 of 10 to the power minus 3 would give us minus 3, so you would have also negative values, but still, we have resolved the problem of having large gap between different values. Covariance matrix, so C is equal to 1 divided by n number of samples, sigma xi minus mu, so difference between current value and the mean of all values multiplied by xi minus mu t, the transpose of that xi minus mu. Eigenvalue decomposition, CVK is equal to lambda k Vk. We've seen that before. Projection onto first m components, Z is equal to Vm, the projected value, okay, transposed value multiplied by x, okay. So transposed m values multiplied by x. Variance explained variance is given by sigma k equal 1 to m lambda k divided by, so it is the difference or the ratio between the m components, okay, the projection components of lambda k divided by the actual components, component values of the dimension, the current dimension. t-SNE or t-distributed stochastic neighbor embedding. It's a little bit complex algorithm. So t-SNE preserves local similarities by converting distances into probabilities. So the distances between values become like probabilities. Similarity in high dimensional space, so Pij, the probability becomes the exponential of the distance between xi xj square, okay, that's the distance, minus, so it's a negative exponent, divided by 2 sigma square, okay, which is the standard deviation, divided by the sigma, the sum of all exponential values, okay, so xi is for the current value. Now, here you have divided by sigma, so it's like the mean of the exponentials, okay? So exponential for I value of minus the modulus xi minus xj, the distance between xi and xj square, divided by 2 sigma square, or standard deviation, divided by the sum of all exponentials of minus xk for k equal 1, 2, 3, etc., minus xl, okay, square, divided by 2 sigma square. All right? Now, similarity in low dimensional space, Qij is given by 1 plus yi minus yj square. This is concerning the outcome, okay? So the outcome probability becomes 1 plus yi minus yj for different outcomes square minus 1, okay, that's the inverse for that, divided by x different to L, 1 plus, that's sigma, okay, sum of O, 1 plus, like distance between different outcomes, yk minus yl squared, to the power of minus 1. The optimization minimizes Kohlberg-Leibler divergence, which is KL, P to K, divergence between input and outcome, given by sigma ij pij log pij divided by qij. t-SNE is mainly used for visualization. Autoencoders. Autoencoders are neural networks that learn compressed representations. So in other words, when you have different range of values, okay, we need to compress them so as to adapt them into an input between 0 and 1, okay? So encoder, z is equal to f theta of x, a function that would turn x, which is the input, into a more normalized, compressed representation of the input. Decoder would be the reverse function that would decode, okay, the value of z to retrieve the x value. So let's say we have encoded yes or no into 0 or into 1 and 0 respectively, okay? The decoder would restore or recuperate the original feature value, the original, in this case, the original label from the encoded label, okay? But it goes the same for the features. Training objectives, L is equal to 1 over n. That's the average between the distance of different values, the current value and the different features, okay? xi minus x hat I, okay? So it would be 1 over n xi minus x hat I, which is the encoded value, so to speak, okay? Square. The latent vector z represents reduced dimensional features. So here we're basically talking about the average, so to speak, between the value, original value of the feature and the adjusted value being the value that has been transformed based on a function. So that distance square divided by n, which is the scale, the total number of samples, gives us L. Latent vector z represents reduced dimensional features. Association learning. This type of learning discovers relationships between variables in large data sets. Okay? Apriori algorithm, it identifies frequent item sets using support thresholds. Support A is equal to the number of transactions containing A divided by total transactions to discover the frequency of item sets, okay, that have the same value, or rather contain the same value, carry the same denominator, so to speak, between them. Confidence for rule A to B, confidence A to B is equal to support of A union B, so the number of transactions containing A and B divided by total number of transactions, all of that divided by support A, which is again the number of transactions containing A divided by the total number of transactions. Okay? Lift A to B is equal to support A union B divided by support A multiplied by support B. So again, support A union B is the number of transactions containing both A and B divided by the total number of transactions. All of that divided by support A, support B, multiplied by support B. Again, support A is number of transactions containing A divided by total number. Support B is number of transactions containing B divided by total number. If lift is greater than 1, it indicates positive association. Okay? Market basket analysis. This type of analysis studies purchasing behavior by analyzing item concurrence. So given transaction set T, Association rules identify patterns A to B, meaning that customers buying A are likely to buy B. This is one of the applications. So, what are the applications? Recommendation systems, such as when you're ordering or you're playing a video on, for example, a video platform, you are more likely to be watching other types of videos belonging to the same category. Retail optimization, so when you're buying this, you are more likely to buy that and that. So I would push the other related items that you are most likely to buy. Just like someone would buy a Coca-Cola with fries, correct? So you would push them both. You would push the second next to the fries, for instance, correct? That would be retail optimization. And targeted marketing. So I would market, or like I would promote a certain set of objects or products next to each other because usually they belong to the same categorical set, so to speak, or they are more likely to be ordered in sequence or together. Finally, unsupervised learning extracts structure from unlabeled data, so we don't have categories predefined for them, through clustering, dimensionality reduction, so you are kind of reducing the dimensions to fit them in specific categories, and association discovery. Algorithms such as k-means, DBSCAN, PCA, t-SNE, and autoencoders reveal hidden patterns, while associating learning techniques such as Apriori uncover relationships useful for decision-making and recommendation systems. Chapter or Module 5, Neural Networks Fundamentals. Neural networks are computational models inspired by biological nervous systems, where you would have a neuron that we will see later, made of axon, dendrites, etc., also called technically in machine learning as perceptron. So they consist of interconnected processing units, which are called the neurons or perceptrons, that learn complex nonlinear mappings between different inputs and outputs through data-driven optimization. Given an input vector x within R, D, which is it's within the real number space in one dimension D, a neural network approximates an unknown function, fx theta, which is approximately equal to y, where theta represents learnable parameters such as the weights and biases that we're going to see in a moment. Biological inspiration. Artificial neural networks, actually the perceptron within these networks, is actually inspired by the biological neuron model within the brain. So multiple perceptrons interconnected together to form the neural network in machine learning. These are actually the networks are inspired by the neural networks within the brain itself. So within this analogy, the biological neuron contains the following: the dendrites, which are the parts of the neuron that connect to another neuron, the soma, which processes signals, it's located here, the axon, which is the transmission line of the signal, so to speak. It connects this neural cell to its synapses. Actually, yeah, it relays the signal to another neuron through these points, okay? And the synapses are like the nerve endings that would be connected to another neuron. And as you notice here, we have a myelin sheath, which like an isolation, the isolation of an electrical power line, okay? An insulation, so that the signal won't be surging to another neuron, okay? To prevent a surge of the electrochemical signal, because it is an electrical signal being transmitted within the brain, of a lesser power, of course. So the axon transmits output signals, but for any transmission line, you'd have an insulation to prevent surge and the loss of signal. Similarly, artificial neurons can receive weighted inputs, so you have a weight being multiplied by the input, compute an activation, so this neuron would fire or not based on the signal it's receiving. Now, it receives from the dendrite a signal from multiple dendrites, signals from multiple other neurons, and it either fires out the signal or not, so it's either activated or not. Just like the binary system, you would have either 0 or 1 based on the weight signal and the bias, by the way, and it would produce an output signal, okay? Computes an activation and then produces an output signal. So an artificial neuron computes a weight sum followed by a nonlinear activation. So you have z is equal to w to the power of tx plus b. W would be the weight vector, so all the weights multiplied by x, input values, plus b. B is the bias, which is the adjustment knob in order to correct the error of a neuron so as to adjust it to produce the favored outcome when it comes to supervised learning. Okay, so as a milder representation, that would be like this is the neuron here. You have the weight that would be multiplied by x1, x2, x3 inputs, correct? Then you'd have a bias, so as to produce z, which is the output value, and z would be inputted to a nonlinear activation function such as a ReLU rectified linear unit or a sigmoid. It would be like that. So if the threshold is in the middle value or above it, it would activate the neuron and the neuron would fire the signal. Otherwise, it would keep the signal. It would not fire. So that leads us to the equation of z is equal w, which is the weight, multiplied by x1, x2, x3. Okay, so w x. And here it is transposed because we have the multiplication of two matrices. Okay, so you would have w1, 2, 3, 4. That is the transpose multiplied by x1, x2, x3. Okay, the transpose would flip the vector vertically plus b. The b is also the vector of biases, so it would be b1, b2, b3, etc. So here you have different inputs, x1, x2, all the way to xn, multiplied by their respective weights. So you have two vectors actually. The first vector of the inputs multiplied by the vector of weights, which is transposed, by the way. Okay, all together added up or summed up, plus the bias, which is the adjustment knob so as to rectify the errors for this algorithm. And z, which would be the output, is directed as an input to an activation function. And for that activation function, when you have the input to that activation, if the value is at a certain threshold for the sigmoid, let's say it's 10h or sigmoid, so if you are above the middle or the average, or right at the middle, it would be fired, it would be activated, and it would produce a result, an output. Otherwise, it would not produce the result. It would stay dormant and it would not fire. And the output would be either 1 or 0, let's say. Okay, so activated or not. So the neuron output is given by y equal sigma, which is the activation function, multiplied by wtx, the transpose of the weights, multiplied by x. Okay, so it's the same thing as saying x1 times w1 plus x2 times w2, because when we're talking about matrix product, okay, you need to have the weight transposed, meaning it's placed vertically all the way to Wn. Then you multiply it by x vector, which is x1, x2, all the way to xn. And the product of both plus the bias would give us the activation. Actually, it would be inputted to the, or multiplied by the activation function, and it would give us the y, which is the actual final output. Okay, so you see here, you have x1, x2, x3, x4 multiplied by weight each. Then it is summed up within this neuron or perceptron. So it is WB plus sigma WI XI. Okay, WB is actually the weight of the actual neuron here. Okay, not the neurons before it. So it would be inputted to the activation function here. By the way, the representation is for ReLU, or rectified linear unit, which is any value below 0 would be inactive, but above 0 it would give us 0.1, 0.5, 1. Okay, that would be the activation, and this is the final outcome. Okay, so inputs, weight sum, activation function, and output layer. Network architecture. Neurons are organized into layers forming a neural network. Okay, so the layer structure. A typical feed-forward neural network consists of the following. The input layer, which is the input side of the network, where you have the ingress of different values that are incoming within the neuron, one after the other, like one wave after the other, in order to adjust the knobs of different perceptrons so as to acquire like the highest accuracy within the outcome. All right, so input layer receives the feature vector, which is the different feature values. Okay, the hidden layers, of course, each time you have one set of values for each feature. Okay, so it would be one wave at the time. So for each input, you would have one value for each feature, each cycle, so to speak, and these values should produce a specific outcome. This is actually in the training phase. You would have one wave after the other of the input values so as to train the model. Then after that, when you give them, when you give the input layer a new set of input values, input feature values, you would get a predicted outcome based on the learning set, okay? Based on the values that the model had used in order to learn, in order to adjust the different knobs within, okay, to calibrate different perceptrons so as to obtain the most accurate outcomes possible. Meaning that the last neuron to fire would lead, would be the one that is connected to the correct output. Now, again, input layer receives the feature vector X. Hidden layers perform nonlinear transformations. Okay, and finally, the output layer produces the predictions or Y hat. In this illustration here, you have at the first stage is the input layer where you have different features going. Okay, so let's say power, temperature, whatever. It depends on what type of prediction we are running, what type of scenario, what type of model. Actually, not the type of model, but what type of prediction. Okay, what is the application for this algorithm? Of course, then you have the hidden layers where the pre-processing, the processing of values runs. Okay, and of course, each one is interconnected to the other ones at each stage, except I didn't interconnect every one of them so as to make it more simple, and quite honestly, because it takes much time. So that would be the hidden layer where the processing of different inputs would happen. Okay, and for each neuron you would have a weight, okay, and W1, W2, W3, different weight matrix multiplied by the x's, which are the inputs here, these are not the values of the feature within the hidden layer. These are the inputs coming from the previous stage, the previous set of neurons. Then you would have an activation function, of course, that would be like the sigmoid, okay, like this one, embedded within the neuron, that would either fire or not. Finally, the outcome in this example would be either yes or no. Okay, so the prediction, the output is either yes or no. Two perceptrons, two neurons, either of them would be activated. The one having the highest weight, okay, would be activated. So if it has a weight greater than 1, greater than 0.5 or greater than equal 0.5, it would be activated. If not, the one having that probability, it's like a probability, okay? The one having a probability greater than or equal to 0.5 would be activated in such case, okay? So if that is the no, then the answer would be no. For layer L, Z of L is equal to weight at neuron, the current neuron, weight of L, multiplied by AL minus 1, which is the activation values coming from the previous layer, plus the bias value, correct? So it is the weight multiplied by the activation or the activations of the previous layer that would become the input for that current perceptron, plus B of L, which is the bias of the current neuron or perceptron. So the activation is given by, now the activation of the current neuron in such case is equal to sigma, which is the sigmoid function, or 1 divided by 1 plus exponential of minus z, okay, of ZL, okay, which is again 1 divided by 1 plus E minus Z if we're talking about the sigmoid function, because you have other activations, which is like the tan-H, tangent, hyperbolic tangent, which is, I think, EH or EZ minus E minus Z over EZ plus E minus Z. Okay, you can verify it. I'm not 100% sure if it's that's it or if I had forgotten it. So WL is the weight matrix of the current perceptron. AL minus 1 is the previous layer activations that become the input for the current layer perceptron that we are analyzing or we are studying here. And AL is the output activation for this perceptron. The final prediction becomes y hat equal fx theta. The activation functions. Activation functions enable neural networks to approximate nonlinear mappings. So you have the sigmoid function, which is sigma of z is equal to 1 divided by 1 plus E minus z. Now, as a plotting, if you want to represent the curve, it goes something like that, if I'm not mistaken again. So above a specific value, you can consider that it has been activated. Otherwise, below that value, it would be inactive. So sigma of z is given by 1 divided by 1 plus exponential of minus z, where sigma of z would be ranging from 0 to 1. Derivative, important for training. So when you're training the neural network, you check the derivative to see how much the slope is, whether it's increasing or decreasing. That's the derivative, actually. So it is equal to sigma z multiplied by 1 minus sigma z to see the gap, okay, between the predicted and the current value. It's like measuring the gradient, used primarily for binary classification outputs. Binary meaning that whether the output is true or false, yes or no. So you have only two discrete values or outcomes at the outputs, okay? Or among the outputs, you have two possible outcomes. This is the binary classification type of algorithm. Hypertan or hyperbolic tangent or tan-H. So actually it turned to be correct. Tan-H of Z is equal to, so it is another type of activation, equal to ez minus e minus z divided by ez plus e minus z. It ranges from -1 to +1. That's the difference, by the way, because the sigmoid starts from 0. It's not defined below 0. Here, it's between -1 and +1. That's the range. Over there, the range was between 0 and 1. So the derivative d tan h z over dz is equal to 1 minus tan h squared z. Advantages, so it is centered around 0, so which gives us an advantage when you have a set of values that can be negative, and it has an improved gradient behavior compared to sigmoid. Okay, so the approximation or the optimization when you're minimizing the error, okay, which is based on actually the gradient, the derivative, okay, because by measuring the derivative, you can perform like a gradient descent, a minimization of the error to measure the gap between the erroneous value and the current value, so it performs better in such case. By the way, the plotting or the curve representation of that tan h would be like something like that. Okay, so it is defined between -1 and +1. Okay, we don't have any definition here, so to speak. All right, so between -1 and +1. ReLU or ReLU for some people, which is rectified linear unit, is equal to max between 0 and z. So ReLU for the derivative value would be either 1 or 0. Okay, actually the representation, so 1 would be for z greater than 0 and 0 for z less than 0. Representation is something like this. So it is defined as 1, or it increases, okay, above for z above 0, z greater than 0, and for z less than 0, it would be 0. Correct? Now, the advantages are the following. Computational simplicity. So, computationally simple. Why? Because it's simply a line, a linear unit. It's not a sigmoid. So, the processing would be much lesser. It would incur lesser weight, lesser strain on the CPU or the NVIDIA chip in such case. It mitigates vanishing gradient problem, okay, and widely used in deep network, because for deep networks, that unit of processing, that activation unit, so to speak, requires a lesser number of resources when it comes to CPUs in order to compute an outcome. So it would be of a better performance, not better performance necessarily, but like it requires less processing, less cooling when you have large systems, large intelligent systems in complex computational environments and in larger neural networks, so to speak. Now here I want to explain a point further, which is the mitigation of the vanishing gradient problem. You see, when we talk about the derivative for the ReLU, it would either give us 1 or 0. It doesn't degrade the way that a nonlinear function such as the sigmoid degrades, rendering us or like giving us a vanishing, an increasing decay, or like an augmented decrease of the value of the gradient, which is the derivative, as you multiply the value forward from one stage to another. So when you have, let's say, 0.5, you multiply it by another 0.5, it becomes 0.025, correct? Or 0.25, so to speak. Yeah, then you multiply it again, so it decreases very rapidly until it reaches 0, so it vanishes, okay? Meanwhile, for the ReLU, it performs better because the derivative gives us 1. Okay? So it doesn't plummet the way a nonlinear function such as the sigmoid plummets, which leads to the vanishing gradient. So the gradient or the derivative gets to a point where it vanishes completely from the calculation. This is what we mean by that. Loss functions. These functions quantify prediction error and guide parameter optimization. So they quantify or evaluate the prediction error, the amount of error we have in the prediction, and also they are like the controllers or the guide parameter for the optimization factor in order to optimize the neural network to increase its accuracy. Given true output y and prediction y hat, training aims to minimize the loss, which is the gap or distance between y, the real value, and the predicted value. This is what we aim for in any machine learning algorithm, to minimize the error, to optimize, meaning to minimize or mitigate the gap, okay, or the loss between predicted and actual real value. So we are aiming to the minimum loss between y, the real value, and y hat, which is the predicted value. Mean squared error. Now we've seen that already when it comes to linear regression, so let's take it up again. Used mainly for regression tasks, LMSE, linear regression, mean squared error, and as it implies, the error here is squared. So it is given by 1 divided by n being the total number of samples, sigma, which is the sum between yi, the current or real value of a prediction, minus the predicted value, which is y hat, at index I, for I equal 1 all the way to n, square. So we are squaring the distance between the actual value predicted and, between the actual value and the predicted value. The gap, we are squaring it in order to blow it up, to magnify the gap, okay? So as to increase the distinction between the different gaps of errors, the different distances, like to increase the gap and make the difference between the actual value and the predicted value more prominent, more distinguished, in order to attain a better accuracy. Okay, so the gradient is given by the derivative of L over derivative, okay, of y hat is equal to minus 2 yi, which is the actual value, minus y hat I. And this, by the way, the advantage of MSE is that it penalizes large derivations or deviations strongly. So when you have values that are way off the correct values, okay, when you have a large deviation, you blow it up. When you're squaring that deviation, it makes it more distinguished, more prominent, forcing you to obtain a much better accuracy, because it's shining the light, like it's bloating, expanding on the error. It's magnifying the error so as to lead to a better, more accurate optimization for a better affinity when it comes to the model performance. Cross entropy loss, used for classification problems, and we have binary cross entropy and categorical cross entropy. Let's start with the first one. L is given by minus 1 divided by n being the total number of samples, times sigma, which is the sum between yi, or the probability for an outcome, okay, multiplied by the logarithm of the predicted outcome, the probability of the predicted outcome, okay, because, by the way, here y is actually a probabilistic value. It's between 0 and 1. Plus 1 minus yi means that the probability of not having that real value. So it's the exact opposite of yi in probabilistic terms. So let's say it's 0.4, 1 minus yi is 0.6. So if you have 40% probability of having that value, so we're talking about the 60% of not having it at all, times logarithm of 1 minus yi hat, which is the probability, the predicted probability of not having that value. This is how it works. Categorical cross entropy. For multi-class classification or classification between different classes, categorizing these classes or like categorizing the different values as different clusters, so to speak, with softmax outputs, y hat k is equal to ezk, which is the exponential of the actual values divided by ezj, sigma ezj, which is the different values within the same category, so to speak. The loss function, L is equal to minus sigma, which is the sum of yk log y hat k. So it is the sum of, so to speak, the cross entropies of different, like for each value, that would be the actual value, yk, multiplied by the logarithm of the predicted value. The sum of that would give us the loss function. Why? Because it's giving you the deviation between the current, or actually the real value, versus the predicted value, which is designated by y hat k. The cross entropy measures divergence. So how much the real value, or actually, to be more accurate, how much the predicted value had diverted from the actual real value between true and predicted probability distributions. Finally, neural networks model complex nonlinear relationships through interconnected perceptrons, also called artificial neurons, inspired by the biological pattern, by biological systems. They employ layered architectures. So you have different layers, the input layer, the hidden layer, which is made of different layers of neurons for processing, and the output layer that would be activated finally to like produce one of the outcomes, okay, or a specific value at the outcome, okay. Now, so nonlinear activation, layered architectures, nonlinear activation, and optimization driven by loss minimization. So you optimize this model, the system, by minimizing losses. Activation functions introduce expansiveness, while loss functions provide learning signals, enabling networks to approximately highly complex mappings, okay, to approximate highly complex mappings. Module 6 or Chapter 6, Deep Learning. Deep learning is about training the neural network, which means adjusting the dials or the knobs within the different sets of layers, especially the hidden layers, in order to attain the correct outcome for each data set input. Because for each set of features, you have a predefined outcome or label when it comes to the training data set. So we know the outcome. We are training or adjusting the dials, the knobs within the neural network in order to obtain always the same outcome. So when tested, it would give us a high accuracy. Let's start with the forward propagation. Forward propagation is the process of computing the output of a neural network given an input vector. So you have an input, okay, for a feed forward neural network with L layers, A0 equal X, so that would be the feature at the entry, no activation. Then you have different sets of activation. So Z of L, which is the output of a neuron in the middle, is given by W vector, different weights multiplied by the different activations from the previous layer. This is why L of L minus 1, plus B, which is the bias value. Okay? L is equal to 1, 2, etc. Okay, for each neuron of that layer, okay, all the way to L, total number of neurons. A of L, which is the activation for that neuron, for this specific neuron that we are at the moment, is given by sigma L, which is the sigmoid function, multiplied, not multiplied, yeah, like the sigma activation for ZL. So ZL would be multiplied by sigma, being the input for that sigma activation function. This is what sigma L times ZL, Z of L means. Z of L is the input for that activation function that would determine whether it would fire or not. So X is the input vector. WL and BL are respectively the weights and bias at layer L. Okay, for each neuron, it has a weight and a bias. So both of them are vectors. Each element for each of the vectors is respectively for the neuron, whether it's a weight or a bias. That would be weight at I, index I, and bias at index I. This would be the weight and bias respectively for that neuron which is at the I position. Z of L is the linear transformation, which is the output right before the activation function for that neuron. Then it goes into the activation function, which is the sigmoid or the 10H or ReLU. Then A of L is the activation, whether the neuron it fired or not. Sigma L again is the activation function. ReLU or ReLU, sigmoid or 10H. It can be one of these. We can have also another type of activations, by the way. Okay, keep that in mind. The final output is given by y hat is equal to A of L, A being the activation, and L is actually pertaining to the final layer. Okay, so it would be the activation result of the final layer. The loss function. Loss function, again, you have the mean squared error. In this case, for the deep learning process, is given by 1 divided by 2m, m being the total number of predicted values, okay, which means total number of features also, okay, multiplied by the sum of the distances between the predicted outcome and the real outcome at each position, okay, for each prediction. So y hat I minus y I, you can have j, k, okay, for different values altogether, or for I equal 1, I equal 2, that would be again the index for each prediction. So it is the distance between y hat and y, or the predicted outcome and the real outcome, which is the square root of y hat minus y square. Okay? And we square that one. So it is y hat minus y square. Okay? Without the square root. Now, for classification cross entropy loss, okay, actually, yeah, it's mean squared error. Yeah, the same thing, okay? So for classification cross entropy loss, JWB here for the loss, for classification is given by minus 1 divided by n, sigma I from 1 to n, k 1 to k, y of k, okay, so for each symbol, for each specimen, okay, sigma yk of I times log yk hat of I. So yk is the real value, y hat k is the predicted value. For k equal 1 all the way to k for all the predictions, okay? And you sum up that for each value, for each input, okay? So for each of the different, or like for each of the different essays. So you have different iterations in the deep learning. I think M here denotes the iterations. Okay, so for each iteration, M, you would have the sum of yk times log y hat k, which is the loss, the cross entropy loss, or the difference. Okay, cross entropy means the difference of entropy, or the data representation between the actual predicted or actual value, actual real outcome that we are trying to train the model to attain, okay, log y hat k, which is the predicted outcome. So it's measuring the gap, okay, the cross entropy between the real outcome and the predicted outcome for all different iterations. Again, to make it clearer, M is the number of training examples, K is the number of classes or categories. This is what we are attaining to. Okay, so it is -1 divided by M, sigma I equal 1 to M, K equal 1 to K, the number of categories, before that the number of examples, YK, which is the real value, log Y hat K, which is the predicted value by the system. Backpropagation. Backpropagation computes gradients of the loss function using the chain rule. At first, the forward propagation is actually the execution that leads us to a predicted outcome. Okay, so it's actually running the prediction to see what outcome we get. Now, when comparing the outcome, and this is during the learning stage of the neural network. So when we get the outcome, and after comparing it with the expected outcome, so the predicted outcome, after comparing it to the real outcome, okay, based on the features, that would be in the test set of, not the validation, yeah, the test set of the data set. So it would be the test rows, the test values, or records, so to speak. So when we compare the real value with the predicted one, and we get an error, we need to adjust the neural network through backpropagation. Backpropagation is the reverse of forward propagation. So forward propagation is running the network from behind, from the input layer all the way to the output layer. Backpropagation goes backwards from the outcome all the way to the beginning, to the features, adjusting the knobs in a way so as to correct the deviations that had rendered us with the erroneous outcome. Because we need to readjust, recalibrate different neurons in different layers in order to get the correct outcome, which is the expected favored value that we were anticipating at the output. How do we actually do that? We start by defining the error term, okay, which is delta L is equal to the derivative, okay, of J over dz. So that would be the error term, which is the deviance, so to speak, the deviation between the correct value and the predicted value. Okay? For the output layer, delta L, which is the error function, so to speak, for the last layer, like capital L is actually the last layer, the output layer, is given by the gradient of the activation L times J, okay, which is the error term, dot sigma prime L, okay, which is the activation, the derivative of the activation of the last layer times Z of L, okay? I know it's a little bit complicated as an equation, but here you're getting how much the error is, okay? We're defining the error value for the output layer. So again, it is the gradient of the activation at the last layer multiplied by J, which is the error value, dot here sigma prime of L, which is the activation derivative for the last layer times Z of L. For hidden layers, it's given by weight, because you have the weight function of L plus 1, okay, times C, which is the transpose of the weight vector, multiplied by the error margin, okay, for that vector, for each term of the vector, by the way, that would be an error vector. Dot here, sigma prime, which is the derivative of like the activation function times z of L. Now let's explain further the model for the error formula for hidden layers, okay, which is sigma or delta L is equal to WL plus 1 T, the transpose for the weight vector, times delta L lowercase l plus 1, times, which is the hammered multiplication factor, okay, the dot product, or which denotes an element to element product, not the matrix product, times sigma prime, which is the derivative of the activation function, times z of L. Meaning of each term. Error term delta L is given by delta J divided by delta Z. It represents the error of layer L, which is the deviance from the actual value, or between the actual value and the expected value, measuring how much the neurons in that layer contribute to the overall cost J. Weighted matrix WL plus 1 within RNL plus 1 times NL. This is the weight matrix connecting layer L to layer L plus 1. WL plus 1 T, which is the transpose of the weight vector, multiplied by delta L plus 1, or the error vector. This term propagates the error from the next layer backwards to the current layer. This is why it's called backward propagation. Now the transpose ensures proper dimensional alignment because we are multiplying two matrices. So the number of lines in the first matrix, okay, should be equal to the number of columns of the second matrix, which is delta 1, delta 2, delta 3, okay? So 3 columns and 3 lines, for example. In order to obtain that, we need to transpose the weight vector, which means that we turn it 90 degrees. This way, it was linear, it became, or it was horizontal, it became vertical, so as to ensure a proper dimensional alignment, okay? Activation function derivative, Z of L is equal to weight L times AL minus 1, which is the activation of the previous layer multiplied by the weight of the current layer plus the bias of the current layer. Sigma prime, which is the activation function of Z of L. This is the derivative of the activation function evaluated at the pre-activation value Z of L. Hadamard product, dot, and circled. It denotes element-wise multiplication, so multiplication element by element, meaning each neuron's error, okay, is scaled by its own activation derivative. The error was the part to the left, okay, which was J times W, correct, times its weight, multiplied to the right, if you remember the previous hidden layer equation of the error. So it is multiplied element-wise by the activation, the derivative of the activation function, which was sigma prime Z of L. Now, derivative using the chain rule. So using the chain rule is like that. Delta of L is equal to derivative of J in respect of Z, L. We can break it down since we have a mediator between them. So you have J and A between J and Z, okay? So we derive in respect of A. So J is derived in respect of A. Then you multiply it by the derivative of A in respect of Z. This is called the chain rule multiplication, or the chain rule derivative multiplication, okay? Deriving according to the chain rule. The word multiplication doesn't fit that much. So it is the chain rule derivative. Since A of L is equal to sigma Z of L, so we can derive them based on A. That's why we can do that. We have derivative of A in respect of ZL is equal to sigma prime Z of L. This is how we obtain derivative of J in respect of the activation function A is equal to WL plus 1t times delta L plus 1. Combining these results, you get the function, which is delta of L, okay, is equal to WL plus 1t, the transpose of the weight vector, times delta L plus 1, okay, multiplied by the derivative of the activation function, because here you have dj over dA, okay, so that would be the activation function, okay, which is sigma prime z of L. Okay, let me retain dA over dz is sigma prime zL. Okay, so dj over dA times dA or dj over dz times dj over dA times dA over dz, correct? dA over dz is the activation function, so we turn it to the next, like you compare them both, you fit them, and you get this equation, all right? So no need to explain it further. You can solve it yourself and obtain the same value. To make it a little bit clearer, all right? So delta of L is given by derivative of J in respect of A times derivative of A in respect of Z, okay? So we are rewriting this equation here. Now, derivative of A in respect of Z is simply the derivative of the activation function, sigma prime Z of L, based on the equation below. So we are left with dz over dA, which is what? That is Wt multiplied by delta, Wt L plus 1 multiplied by delta L plus 1, which we've seen it before. So all of these together would give us the formula for the error that we've seen on the next page, which is WL plus 1 T delta L plus 1 multiplied, that's dj, okay, dj, okay, dj I will call it, over dA, derivative of j in respect of A. This is the part, multiplied pointwise, like point to point, by dA over dz, which is actually the derivative of the sigmoid activation function at ZL, okay, in respect of ZL. So the gradients, dj over dw equal delta L, AL minus 1t, dj over dB equal delta of L. Gradient descent. Gradient descent updates parameters in the direction of the steepest descent in order to minimize the error. This is actually the calculation we are running in such scenario. So the weight is given by weight minus eta gradient of j. So we're trying to minimize the error again, okay, so as to obtain a zero slope. W represents the model parameters, not necessarily the weight here. Eta is the learning rate, so how much further each step is from the step before it, from the point value before it. And gradient of JW is the gradient of the loss. So we'll run a small example. Let's say here, this is the error function. Okay, so when you have a stabilization here, meaning that when the slope is 0, there's no longer a descent. So we've attained the minimum error value. How do we get there? The learning rate is actually the length of the vector traveling downward between 2 points, okay? So that would be the learning rate, or the size of each step, okay? So as long as the slope is negative, it means that we're still minimizing the error value, okay? So again, now eta is the learning rate, which is the distance or like the size, the length of this vector. Gradient of JW is the gradient of the loss, so that would be defined by how steep the descent is. Now, once the slope becomes 0 or proximate to 0, then we would attain the minimum loss value. Okay? If the system is stable, if we don't have another plunge here into another value, even lower. Okay? Now, so when we attain a slope which is equal to 0, it means that we have attained the minimum error possible, and that would be the most optimal adjustment for the neural network model. Okay, so we had minimized the errors, and in this way the model can generalize better. Okay, we have optimized, to place it simply, optimization algorithms that stem from the same concept of the gradient descent. You have at first SGD, or stochastic gradient descent. Instead of using the full data set, okay, it would be W equal W minus eta gradient JI So this is the gradient descent as we've seen it moments ago, where JI is the loss for a single example or mini batch. Okay, so we reduce the data set into batches. We don't examine the entire set. Okay, but we step over from one value to another. So we increase the stepping. Eta is the step size, how much you're going further. Now, if the step is too long, by the way, you can get an error. Okay, we can overshoot the minimum value. To give you an example, so let's say you have a curve like that, okay, and the step is like this. Okay, so the next time you step over, okay, you see that since the step size is very large, we have overrun or overshot the minimum, the desired minimum. So the minimum is still below, but we have overshot it. That's why we should balance between resolution and performance of the model. We should not also be placing more strain on the CPU, because the model would be running much slower. Okay, if you have a lengthier step size like this one, the computation would be required, would be lighter, so the computation would run faster, except the result would be less accurate. But if we minimize the size of the step, let's say the step is much smaller, so the number of steps taken, the number of iterations that need to be run by the algorithm would be much larger, so they would require much higher CPU performance and strain. Okay, you would need more CPU resources in order to run the model. That would be the drawback, and it would take more time to converge and to compile, so to speak. So JI is the loss for a single example or mini batch. Mini batch gradient, for each gradient, the mini batch gradient is given by 1 over B, which is the batch size. This is when running this error validation model, okay, the gradient descent SGD on batches. Batches meaning a fragment, a chunk of the entire set. Okay? So we take samples of the set. We don't run it on the entire set. So mini batch gradient is given by 1 over the size of the gradient times sigma of gradient JIW, which is the JI being the loss for each specimen of that batch. Okay? Exactly. Momentum. The momentum accelerates convergence. So it's given by Vt equal beta Vt minus 1 plus 1 minus beta gradient JWt. And Wt plus 1 is equal to Wt minus eta Vt. Vt is the velocity. So it can reflect, it's reflecting the rate at which you are measuring or testing the different specimens. Beta is a value between 0 and 1, is the momentum coefficient. Okay, it is the momentum coefficient. Adam optimizer. Adam algorithm combines momentum and adaptive learning rates. So it is combining between the momentum, the velocity or speed at which you are taking or getting different specimens, and the learning rate, which is a function of the step, the eta step that we've already touched upon or talked about. So MT is given by beta 1 MT minus 1 plus 1 minus beta 1, okay, times GT. Velocity is given by beta 2 Vt minus 1 plus 1 minus beta 2 GT squared. The bias correction is given by MT equal MT divided by 1 minus BT1. Vt equal Vt minus Vt divided by 1 minus beta T2. The update rule is given by Wt plus 1 is equal to Wt minus eta, which is the learning rate, times m of t divided by the square root of the velocity plus epsilon, which is like a distance value, okay, distance margin. Now, as a further explanation, Wt plus 1 would be the updated value of Wt, which is being adjusted based on a learning rate of eta multiplied by a bias correction of m of t divided by square root of Vt, which is the velocity of recurrence, plus epsilon, which is also a bias-related adjustment factor. Regularization. We have the concept of the dropout in order to avoid overfitting, because we cannot have the system, the neural network system, learn the entire set of values. Okay, we need to drop out some values to increase the degrees of the freedom of the system, so to speak. Drop out randomly deactivates neurons during training in order to simplify the model and reducing the overfitting, okay, or avoiding the overfitting. R of L is like directly proportional to Bernoulli probability. This is how it works. A of L, which is the activation function, is equal to the random function multiplied by A of L. So if this randomness, which goes between 0 and 1, if it's 0, the activation would be dropped out, otherwise it would be validated. Where P is the key probability of keeping the activation of the function, or like the functionality of a neuron. If it's 0, you are bypassing that neuron and deactivating it, so to speak, in order to minimize the complexity again of the neural network model and to avoid the overfitting of the model to the actual like to the entire data set that's being learned. AL of test is equal to the probability multiplied by the activation function. Batch normalization. Batch normalization normalizes layer inputs. So you have mu b, which is the mean of the batch, is equal to the sum of all the values within the batch, all the values of a feature within the batch from I equal 1 to m, divided by m, which is the number of values, the number of samples. Sigma square b is the standard deviation squared, which is 1 over m sigma xi minus mu b squared. Okay, again, the standard deviation. The normalized value is given by xi normalized is equal to xi minus mu b minus the median or the mean divided by the square root of sigma square b, which is the standard deviation. So it is sigma b, the standard deviation, plus, okay, but plus an epsilon value, which is like a factor added as a bias, okay, as a regulation. Scale and shift given by yi equal to gamma times x input plus beta, where gamma and beta are learnable parameters that can be adjusted in order to calibrate the neural network model to increase its accuracy and performance. Finally, deep learning training consists of forward propagation to compute predictions, back propagation to compute gradients, gradient-based optimization to update parameters, and the regularization techniques to improve generalization. Chapter or Module 7, Recurrent Neural Networks, or RNNs. So, at first, let's start with the concept of a recurrent neural network and how it works. We will start with the sequential data. What is a sequential data and how does it relate to the RNN concept? Sequential data consists of ordered observations based on a timeline. So you have present and past values that will dictate a future value. So based on these, we will predict a future outcome. And the order in this set carries meaningful information. Given a sequence, for example, x is equal to x1, x2, all the way to x of t, where t would be the last value that has been measured. Each element depends on the previous element. This is the sequential data. Just like series in mathematics, okay, or sequences. So the current value depends on previous values or past values, and the future values depend both on present value and past value. Time series. So what is a time series? A time series is a sequence indexed by time. So it is changing in respect of time. So x of t is, or belongs to a space of real numbers within a specific dimension d. T equal 1, 2, etc. all the way to t, which is the final time of recuperation of the last value. Goal is to predict the future values. So the future values are based or actually depend on the previous and the present value. So x of t plus 1, which is the future value to be predicted, is a function of all the previous or the past values, along, of course, with the present value. Autoregressive modeling is given by x of t is equal to the sum of ti xt minus I, which is implying all the values that are past tense, plus epsilon of t, which is the noise of the current time. Okay, this is a noise parameter that will affect the accuracy and the recuperation of the current value, so to speak. Language modeling. Given a sequence of words, W1, W2, all the way to WT, and these different words are placed one after the other in sequence, like within a sentence, for example. Definitely within a sentence of words, a meaningful phrase. The language modeling estimates the probability of that sentence being the sequential allocation of the words in that exact order, so to speak. So probability of W1, W2, all the way to WT, probability of that sentence occurring, or in other words, of the placement of the words one after the other in this sequence happening or occurring, is given by the probability of WT. So it's the product, okay, from t equal 1, from the first allotment, so to speak, the first word, okay, the first occurrence, all the way to t, which is the last occurrence. So it's the product of the different probabilities for each placement of the word, or the placement, probability of placement of each word right after the other in that same sequence. Okay, so let's say probability of I'm going home, for instance. It is the product of the probability for I coming first, then probability of M, then probability of going, the verb, all the way to home, being placed in that exact sequence. Neural networks approximate, so probability of WT for W1 all the way to WT minus 1 is given by the softmax function WHT plus B, where HT is the hidden state at time t, and B, of course, is the bias. RNN architecture. Standard RNN updates hidden states recursively, okay, in a recursive manner. So H of t, which is the hidden state, is given by phi of WXH xt, the weight times the value, plus HT minus 1, which is the previous state. So that would be for the current state, weight times x of t, the current value, plus the previous weight times the previous state, again, the previous value, plus b of h, which is the bias. Output is given by y of t is equal to why times ht plus by, where x of t is the input at time t, h of t is the hidden state, and phi is the activation, such as the tan h, hyperbolic tangent, or the redo or rectified linear unit. Now, to better explain how this works, h of t is actually a summarization of the past values, okay? This is the hidden value. H of t, the hidden value, represents a summary of the past values based on which we are predicting or forecasting a future value. So it plays an essential role in the prediction algorithm. Now, it is given by phi wxh xt, okay, which is the weight, times xh times xt plus whh ht minus 1, so these pertain to the past values, plus bh, which is the bias value. Output is given by y of t is equal to why, which is the weight, times h of t, okay, the past value, plus by, which is the bias value. Again, now the training minimizes the sequence loss. This would be j, this is the loss, is equal to the sum from t equal 1 to capital T. So throughout all the sequence, from the first word all the way to the last word, so to speak, it is the sum of losses between, which is the divergence or differentiation or the gap between the actual value, the actual outcome, and the predicted outcome. Very similar to what we've seen before. Backpropagation through time, or BPTT, computes gradients. So that would be the derivative of j over, or in respect of WHH, is given by sigma of t equal 1 to t. So it propagates backward through time, or through the past values, so to speak. Okay, it is the differential of j over the past value, so it's the error in the past value multiplied by the derivative of the past value in respect of WHH, okay, in respect of its weighted value, so to speak. Vanishing gradient problem during BPTT, which is backpropagation through time, through past values. Gradients involve repeated multiplications. Now, through these multiplications, when you have a value that is less than 1, normally it would decay quickly to 0. So dj over dht, that is the derivative of the error margin in respect of past values, is given by the product from k equal t all the way, lowercase t, all the way to big T, which is traveling through all the past values all the way to the last value of these, Okay, WH, T, the transpose of the word, times the diagonalization, or yeah, the diagonal of P prime ZK, okay, times dj derived like over dht, which is the error differential in respect of the past values. So if eigenvalues of WHH are less than 1, gradients vanish quickly. Why? Because you are multiplying a number or a value less than 1, so it decays quickly towards 0. Now, if it is greater than 1, then the gradients explode. They go to infinity. They rise all the way to infinity. Now, attempting to simplify a little more this function, what's happening here. So again, the differential of the error function, okay, or the derivative of the error function, in other words, how the error is changing in respect of past values, this is equal to the product for all the values from the first word all the way to the last word of the past values, because they are sequential. The product of each word value, okay, multiplied by the diagonal matrix of phi prime zk, which is the activation function. So in other words, for each word you are multiplying by the activation function, okay, that is respective for that word position. All of that would be multiplied again by the derivative of j, okay, derivative of j, which is like the differential of the error in respect of the last value, in respect of the last past value among all the values. So this is deriving the error in respect of all past values in general, like as a variable, as a function. It is given by the product of different words, okay, values multiplied by their respective activation functions, times the differential of the error function in respect of the last past value, the last one alone. Advanced models. Let's start with LSTM, or long short-term memory. LSTM introduces gates to control information flow, just like a valve does with a hydraulic or within a hydraulic system to control the flow of a fluid within a pipe. Okay, you have the forget gate, which is given by Ft is equal to sigma, which is the activation function based on these memory terms, Wfxt plus Ufht minus 1, which is again the past value. Okay, it is pertaining to the past value. Wf is the memory of the word value times xt, which is the current input value, plus bf, again, which is the bias. Input gate is I of t is equal to, so forget gate meaning this gate would drop a value, okay? It would drop a current word, so to speak. Input gate given by sigma activation function Wix(t), so the current memory of the word times xt value plus Uiht minus 1, again the past value, plus bi, so it would be the bias at that exact point. Candidate memory is Ct is equal to 10h, so it would be activated by a hyperbolic tangent of Wcxt plus Ucht minus 1 plus Bc, and cell state update is given by f of t, which is this first one, forget gate, multiplied by Ct minus 1 minus the candidate memory, okay? Ct minus 1 plus I of t, which is the input gate, multiplied by Ct. So the forget gate multiplied by a past value plus I of t multiplied by the current value, the current candidate. Output gate is given by OT equals sigma, which is the activation function of Woxt plus Uoht minus 1 plus B0, okay, BO. or BO meaning B output. So again, the same concept here. So it is WO, which is the memory value of the word times x of t, the current input value, plus UOHT minus 1, the past value, okay, like past summary, so to speak, plus BO, which is the bias at the output. Hidden state h of t is equal to OT, okay, so the current hidden state is given by the output value dot product, the tan h, which is the hyperbolic tangent of the CT, okay, which is the current candidate. This structure mitigates vanishing gradients. So it subsides the vanishing gradients or gradients like depleting all the way to 0. Second, GRU. GRU simplifies LSTM with two gates. You have the update gate given by z of t is equal to sigma wz xt plus uz ht minus 1. And the reset gate, RT, is given by an activation function sigma wr xt plus ur ht minus 1. Okay, with an R probability for reset. Candidate state is given by h of t equal 10h wxt plus u rt dot product ht minus 1. All right, so it will reset based on RT probability, so to speak. Final hidden state is given by 1 minus zt, okay, dot ht minus 1, which is the past state value, plus z of t dot product h of t, okay, the candidate state. GRU are computationally efficient while addressing vanishing gradients. Okay, again, so h of t, which is the current hidden state, is given by 1 minus z of t, okay, which is the update gate. So it is the probability of not updating multiplied by the past state, past hidden state. Okay, so it is the actual upkeep of the past state, so to speak, plus z of t, okay, which is the update gate value, multiplied, or the update function, so to speak, multiplied with a dot product all the way with h of t, which is the current candidate. H of t minus 1 is the past candidate. Applications. So what would be the applications for that kind of algorithm or RNN? First, speech recognition. So for example, by converting acoustic signal x of t into text, so probability of y in respect of x is given by product from t equal 1 all the way to capital T throughout all the sequence of the wordings. Okay, it is the product of py of t multiplied by h of t for each t value. Okay, probability of y of t, which is the actual value, being equal to a past or a hidden state value. Okay, now often trained with connectionist temporal classification CTC. So LCTC, which is the loss function, is given by minus log probability of y given x. Second, machine translation. So you have sequence to sequence model. The encoder would be hidden state ht equal RNN encoding xt ht minus 1, which is again, so it is the input at a specific time and being encoded into a past state, past hidden state. So decoder would be reversing that order from a current value, or like the decoder is reversing from the past value into the current value, where C is context vector, conditional probability, so py x1 all the way to t, x1 all the way to t is given by the product of y of t. Okay, this is the desired outcome in respect of x, which is the input. Forecasting is actually predicting future values based on present and past values. Okay, so it is given by x of t plus k, which implies a future value, is given by a function of all the past and the present values altogether. Loss function MSE is j equal 1 divided by t sigma t equal 1 to t x of t minus x hat of t, so the current, or actually the real value minus the predicted value square. Okay, this would be the loss function, the mean square error. Okay, mean square error. Now, the stock prediction is one of the applications, the weather forecasting. So you minimize the loss by minimizing j here. In other words, we try as much as we can to fit the prediction function in a way so as to mitigate or to coerce the gap between the predicted value and the actual value. The word there is not coerce, but to narrow down, to narrow down the gap or distance between correct value or actual value and the predicted value. The same concept that we've seen in other types of algorithms. And again, the prediction is dependent on the sequential values that are collected in the past, that were collected previously. These are what we base the entire measurement upon in order to project a future value. Finally, recurrent neural networks, they model sequential dependencies, use shared weights across time steps, suffer from vanishing gradients. Okay, why? Because due to the fact that the product is being multiplied, you can get very fast to a zero value. And they are improved by LSTM and GRU architectures. They are widely used in speech, translation, and forecasting tasks. Module 8, Natural Language Processing, or NLP. Okay, here we're talking about text processing. The NLP, or Natural Language Processing, focuses on enabling machines to understand text, interpret, and also generate human language-based text. First, tokenization. Tokenization is the process of splitting text into smaller, more digestible units or tokens that would form the basic foundation for that text. So, given a document, D equal natural language processing is powerful, which is only this one sentence. The tokenization produces word 1, word 2, word 3, all the way to word N. Okay, so you are breaking down the entire document into smaller words, smaller chunks that are more controllable, more digestible, easier to process. Okay, these would become the basic units for the entire language. Mathematically, we define a tokenizer function, which is given by S, that would produce W1, W2, all the way to Wn. S being the set of all strings or all sets of characters that are attached in a word format. Okay? Strings of characters, like a string actually is a word, technically speaking, in the computer language. For subword tokenization, so when we're talking about a word being split into two more basic words, okay, e.g. byte fair encoding, the vocabulary is constructed to maximize likelihood, all right, in order to maximize the matching between a word, like a lower, a subset of word, okay, a word subset, and an actual value that we have set aside for comparison, okay? So it would be these values that would be compared to like the basic elements or tokens. This is how it works. So where S is the set of all strings for subword tokenization byte fair encoding, the vocabulary is constructed to maximize likelihood. Max V of sigma log P probability of D, okay, for the document to have a V value, which is this subset token. Stemming and lemmatization. What do these two words actually mean when it comes to NLP case, the natural language processing? So, stemming reduces words to their root form, the most basic form, based or via heuristic rules. Heuristic, this term means approaching a problem to find a solution based on the shortest path. So, by following, in other words, a shortcut and the most practical way to get a solution, a result. However, it might not necessarily be the most optimal one. So here in this case, so you see running becomes run. This is what it means in this scenario, okay? The heuristic rule is actually finding the most basic form of the word running, which is run. So the word run seems to be a more like the most reduced form of this block word running. So this is the root word. This is the root verb, so to speak. And ing is actually an extra. It's an add-on, but the verb itself is to run. Lemmatization uses vocabulary and morphological analysis. So you have the vocabulary, meaning that, let's say, you have better, okay, is another word for good. So it seems to be an adjective for good, although the machine would not understand that, but it would associate the occurrence of better in the same way that the word good is occurring. So there's a very close association between these two words. They seem to be synonymous. And morphological analysis is what we've seen in the previous sentence, where running is the same as run. However, run is a shortest form of running, being the adjective. Okay? Or like, I don't remember what do they call it, like the participle, past participle, something like that. Or like the word, actually the word. Formally, L is given by W, word, that it is transformed to a lemmatization format or version for W. Text representations. Let's start with bag of words. So a document is represented as a frequency vector. Let vocabulary size be V. X is equal to x1, x2, xv, where xi would be the count for each word wi within the document. Okay, so x1 is the number of occurrence for the first word in the document, x2 for the second word, x3 for the third word, etc. Okay, how often each word is occurring within the document, that would be the frequency vector. Okay, in other words, the number of occurrence of words, of each word within the entire full document. And it ignores the word order in such case. Okay, the frequency vector. TF-IDF, or term frequency inverse document frequency. TF, which is the term frequency, is the number of terms occurring in respect of the total number of terms. Okay, so it is the frequency of occurrence or the number of occurrences of a specific term that we are measuring the frequency for, divided by the total number of terms within the entire document. So TFTD is equal to the count, or counting actually the number of occurrences of the term within the document divided by the total counts for all terms within the document. IDF, or inverse document frequency, is given by IDFT. So it's like the inverse Fourier transform in some way. It is equal to log or logarithm or n, with n is the number, total number of documents, divided by 1 plus DFT, with DFT is actually the number of documents containing term t. Now, TF-IDF altogether is equal to TFTD, which is the term frequency, multiplied by the inverse document frequency, the frequency of the term occurrence within the total documents. Word embeddings. Word embeddings represent words as dense vectors in RD, okay, R space in D dimension. So basically the mapping is between the word and the vector of this word. So again, the mapping, what it actually does is that it maps the words to a density vector belonging or representing that word, okay, in R space dimension D. Skip-gram objective, it is given by the maximum of the sums of, or the sum of the log p, logarithm of the probability of occurrence of wt plus j. So probability of occurrence of a word after a certain time, okay, with j being a varying index from a minus c, which is, the lower candidate, to plus c, the upper candidate. The softmax probability is given by p w0 wi is equal to the exponential of the density vector for w0, word 0, the probability for the word we are searching, okay, among wi's, t transposed matrix for that vector, times vwi, okay, for each word, divided by sigma w within v, within the v vector, exponential of vwt, okay, vwi. Embeddings capture semantic similarity, so similarity wi wj is given by vi dot vj, so this is a dot product, okay, between the vector for the word I and the density vector for the word j, divided by the modulo of vi times vj. So this is actually a, dot product of the vector, so to speak. Yeah, exactly. So it can be written like that actually. It's equal to vi vj. This is the product to see how much length is there for the vector that is normal, okay, to the two vectors vi and vj. Actually, another representation for that would be vi times vj times sine theta, okay, the sine of the angle between these two vectors. Okay, so it would be vi times vj times sine theta. Okay, to explain it now a little bit further. So the probability here is the probability for the word output, okay, given an input center wi. It is equal to the exponential, which gives positive values, for the vector of the output word, okay, transposed in order to multiply it by the other vector for the word inputs. So it is like this dot this, okay? We are multiplying a vertical vector with an horizontal vector so as to make it like a count or work out as an element to element product, okay? Divided by sigma, which is the sum for the exponential of VWT transpose for VW multiplied by VWI, which is the vector for all, like for the input values, okay? So multiplied by the transpose of VW, which is the vector for all words, okay? So it is a probability comparison. This is how the softmax works. Probability comparison between the output word desired divided by probability for occurrence of all the other words, okay, total words. Embeddings capture semantic similarity. Again, the similarity is given by this factor, this product here. And again, now, if they are completely similar, like if they are, if the angle is 0, okay, so sine 0 is 0, thus the product here would give us 0. So they would be completely like on the same direction, okay? So the product between them would be 0. They need to have an angle between them. This is how you get another value or a value other than 0. Modern NLP. Let's start with attention mechanism. Attention allows models to focus on relevant parts of the input, okay, by like giving more focus on the input, so to speak. Giving queries Q, keys K, and values V. So Q is the query, the keys are K, represented by K vector, and the values are V. The attention for Q, K, V, okay, attention given to the query having keys K and values V is equal to the softmax probability of Q multiplied by KT, which is the transpose of K, because we are multiplying again two vectors. So in order to force them to be multiplied, not in a formal matrix multiplication, but instead in a mode or a style of element-to-element product, okay, we need to transpose the other vector that's being multiplied. So Q multiplied by K, point to point or like element by element, divided by the square root of dk, okay, and dk is the key dimension, okay, multiplied by V, which is the vector for values. This enables dynamic weighting for the attention, okay, dynamic weighting for each word to give focus for specific more prominent words more than others. Alpha ij is equal to the exponential of eij divided by sigma k exponential eik, okay, this is the weighting here in this case, just like we've seen it in other algorithms. So it's the same pattern, but it changes based on the application, which is here the modern NLP. Transformers rely entirely on self-attention, okay? So what is self-attention? It's given by the softmax function of xwk multiplied by xw big K, so the words of query, multiplied by x times the words for keys, okay, the transpose of that, of course, to have an element-to-element multiplication, divided by the square root of dk, which is the dimension keys, multiplied by xwv, which is the vector of weight, okay, for the values. So here, yeah, w is the weight, rather not the word, okay? I might be using them interchangeably, but here we are meaning, or we are referring to the weights for the values, for the keys, and for the queries. Now, multi-head attention, multi-head QKV is equal to the concatenation of different heads, okay, times the word of the output word. Positional encoding is the encoding of a word based on its position in the phrase. So PE of position, a certain position, like a geographic location within the phrase, okay? So the word is at the first, second, third position, etc. At 2i, okay, it's like a unitary vector here. So it is equal to sin of, or sine, if you want, of the position divided by 10,000 to the power of 2i divided by d, with d being the dimension, of course, and I being the index. PE position of 2i plus 1, which is for an element right after that, okay, is equal to cosine position divided by 10,000, okay, 2i divided by d. Okay, so if it's at position 2i plus 1, so you would shift to cosine. Okay, by the way, because the cosine starts from 1. So when I equals 0, cosine is 1. But sine would be 0 in such case. If I is 0, okay, is the value, if the value of the sine is 0, the sine, like if I is 0, sine of 0 would be 0. If the position is 0, so to speak. All right, so this is like a small difference between the two formulas. Large language models, LLMs. LLMs are large-scale transformer-based models trained on massive corpora, massive amount of information, and the next token prediction is based on this formula. This is the training objective. It is the maximum from t equal 1 all the way to capital T, so from the first value, previous value, to the last previous value, okay, in sequence, so from the first value all the way to the last mentioned value, we are going through that kind of journey through all the previous or past values in order to predict the future value. Okay, the value of the future to be predicted, so the next token would be the log of, or based, it would be chosen or selected based on log p theta, probability of at theta of the word t, which is the current word that is expected to occur in the sequence, based on all the words that are before it, that are less than t, which means that they had occurred already in the past events. Probability via softmax is given by probability Wt given words that are less than t, that had occurred previously, is equal to softmax Wht, with ht being the hidden statement for the current word. In the same way, we have the loss function cross entropy given by L equal minus sigma t equal 1 to t log pw, probability of the word t for all the words that are less than t. The scaling law, which is an empirical relation, is that the loss for a number n of documents is directly proportional to n to the power of minus alpha, with alpha being the weighted function, the weighting function. N is the model size or data size, in other words. Finally, NLP or natural language processing involves text preprocessing, tokenization and normalization, feature representation such as the bag of words, the FIDF embeddings, and attention-based architectures to focus on specific words, to highlight specific words. Transformer models also powering modern LLMs, large language models such as ChatGPT. Module 9, Reinforcement Learning. So what is RL or reinforcement learning? It is a machine learning approach where an agent learns to make a decision based on a penalty reward system. So it interacts with an environment and it receives feedback whether an action was good or bad, so whether it is penalized or it is rewarded. Okay, and the reward penalty system is what actually makes this agent learn, this software agent learn. The goal is to learn a strategy that maximizes the rewards while minimizing or reducing almost completely the penalties. Okay, so you need to aim to maximize the total reward over time. The RL or reinforcement learning works through trial and error. In other words, the agent repeatedly observes the state of the environment, takes an action. Now, if the action receives a reward, then it is added to the sequence of actions that need to be taken that are positive. Okay, it is adopted as a protocol, so to speak. So now that is given if the reward is positive. Now, if it's a negative, which means it was a penalty, then that action would not be taken next time. Okay? Updates, like, yeah, the agent would update its strategy based on the reward system to make better decisions next time. Over time, the agent learns the best rewarding sequence of actions in order to produce the long-term outcomes. As an example to that is actually the video games. Okay, in the gaming, let's say you are teaching an agent, a player, which is a computer player, to win in a game. Okay, let's say Super Mario. So it needs to repeat the same stage over and over, and at each time, at each moment, decide whether the action to be taken had the last time given him a reward or a penalty. If it was penalized, he would take another action. Otherwise, he would take the same action and move on to the next stage. Now, if he falters or fails in the next stage at a specific turn, at a specific position within the environment, he would reassess the next time and take like another action. All right? So, again, it is based on a reward system. Based on the rewards, he would add the action on the sequence of the actions to be taken as a protocol to be executed in sequence next time. Otherwise, if it was penalizing, then he would choose another action the next time he gets to that stage until he masters the entire game, so to speak, or the entire stage, if we're talking about one level. Now, RL again is a learning paradigm where an agent interacts with an environment to maximize cumulative reward. The RL problem is commonly modeled as a Markov decision process, or MDP, okay, like Markov chains. So M is equal to SAPR gamma. Now, what are these different variables that the decision would depend upon? First, S is the set of states. A is the set of actions, so set of states that the player is going through. A set of actions that are available, for example, shoot, jump, crouch. P is the transition probability from one state to another. R is the reward function, which is either penalizing or like positively rewarding, so success or failure. And finally, gamma is the discount factor between 0 and 1. So whether a part of the set or the decision should be discounted or not, okay? Should be disregarded or not. At time step t, the state S of t transitions into the next state st plus 1 after the action by the agent has been taken, and the action being A of t, which is the action taken at the current state S of t. Now this would produce a reward R of t at time t given by R of st at, so it's a reward that is dependent, or it's a function of S of t, the current state, and the action taken at that current state. The objective is to maximize the expected cumulative discounted reward, so GT is equal to sum from 0 to infinity, gamma k, so gamma would be flipping, that's the discount, okay, between 0 and 1. R of t, so multiplied by the reward at time t, plus k meaning that at each trial, at each action, at each state, whenever an action is being taken, whenever an action is taken, you would get a reward, whether a positive or a negative reward. And then we sum up, or we add up all the rewards in order to assess for this type of scenario, for this type of sequence of actions, okay, or mode of operation taken by the agent. How much is the overall reward? Is it a good reward or bad? And this way we can decide, like the agent would decide to go in a different way, or to change some parts of would change or would alter some sets of actions in order to attain a better reward. So the main purpose is to maximize the reward, and this will determine the quality of play and the performance, so to speak, of the entire model. Agent. The agent selects actions based on its policy, okay? So policy or protocol. This is what the agent does. The agent is the one controlling the pundit, the player within the game. So A of t action is proportional or given by P of S of t. So it is an action taken in a specific time for a state, for the current state. The agent's goal is to maximize the reward, okay, which is EPGT. Environment, the environment is the play atmosphere, like the playing space, okay? It defines the state transitions. So, probability of a transition to another state, which is ST plus 1, given the current state, ST, and an action A of T, it provides feedback via reward signals. Now, the state, by the way, is whether the player had moved forward or not, whether he's dead or alive. This is what the state entails, the current status of the player. The reward is a scalar feedback given by R of t is equal to R, ST, AT, ST being the current status and AT being the action taken at that status. Okay, so based on the action, you would have a reward, whether negative or positive. Okay, it can be positive reward or a penalization. Design of R significantly affects the learning behavior. So how you design the reward system, it surely will affect the learning behavior. So you should only penalize when necessary, so to speak. Otherwise, you would cripple the learning process of the agent within the algorithm. Key concepts. 26.1, policy. Okay, a policy defines action selection. What action should be taken, okay, based on the premises of the policy. This is the policy. So it is given by A equal P of S, which is a set of rules that will determine the type of action to be taken, so to speak. Now, stochastic policy is depending on a probabilistic approach, okay, rather than the other type of selection. So it would be a policy based on the probability of taking a specific action at a specific state. Value function, state value function is given by VPS is equal to EP, GT, which is the reward, S of t is equal to S, which is, okay, like the status at time t is equal to S. Action value function, Q function, is given by Q pi SA, okay, S being the status, A being the action, is equal to E pi GT ST, okay, so it is based on the reward. ST is equal to S, the current state is S, and current action AT is A, okay. The Bellman expectation equation, so VPS, which is the state value function, is equal to sigma, the set of actions taken, times the probability for a specific state to be produced based on that set of action and the current status, multiplied by the reward system SA, okay, plus gamma, which is like the drop function again, the drop factor of the value VP for S prime, which is like the expected status. I know it's mouthful, it's a little bit complex. I'm trying to break it down as easy as possible. Bellman optimality equation is given by Q star SA is equal to sigma or sum S prime, okay, probability of a specific status to occur in the future based on the current status and action taken, multiplied by the reward SA plus gamma, which is the drop factor, times the maximum of the quality, okay, or like maximum of the Q factor for the next status, okay, for the next status based on also the next action in the future. Q learning. Q learning is a model-free RL or reinforced learning algorithm that learns the optimal action value function, okay? So optimal value function QSA learn based on QSA plus alpha, okay, which is the learning rate, by the way, multiplied by R, the reward function, plus gamma, the discount factor or the drop factor, times maximum of Q S prime A prime minus Q SA. okay, minus QSA for the current status or current state and action. Max X A prime QS prime A prime is equal to the estimate of optimum future value. The greedy policy derived from Q is given by P star S is equal to argmax, so the maximum argument for the optimal value Q, okay, that is a function of S and A, current state and current action. Applications, one of the applications is robotics because they learn to walk and to do activities based on trials and errors. RL enables robots to learn control policies by P star AS equal argmax EP GT, in other words, maximizing the rewards. Applications include manipulation, locomotion, and grasping tasks. Game AI, agents learn strategies through interaction. Example objectives, so max EP of sigma gamma t, which is the drop factor again, times RT, the reward function, used in board games, video games, and competitive simulations. Autonomous navigation, like cars self-driving. RL enables decision-making under uncertainty. State may include position and sensor readings. Okay, S of t is equal to xt, yt, theta t, and sensors. Now, the reward encourages safe and efficient travel. Okay, R of t is equal to minus collision penalty plus goal reward. Finally, the reinforcement learning is formulated as an MDP. It uses policies to select actions, evaluates actions via value functions, learns optimal strategies using algorithms like Q-learning, and is widely applied in robotics, gaming, and autonomous systems. Finally, thank you so much for watching this video, and God bless you. So grateful whether you've watched it all or you've watched parts of it. And as a side note here, machine learning is invented by men. It should not be replacing God. It is not God. You should not be taking advice from a machine learning system, okay, such as marriage advice or counseling or whatever. Use it wisely. It should not be a replacement for God. Otherwise, it becomes your idol. It becomes your own God, okay? And it becomes dangerous. You probably have at this point heard about the person who had almost committed suicide because of the AI had told him to divorce his wife. So it should not be a replacement to God. I believe in the God of the Bible. I believe in Jesus Christ as Lord and Savior. But I also love technical stuff. This is why I'm explaining this presentation. This is why I'm teaching this. So use it wisely, okay? And in whatever you need, after you have given your life to Jesus Christ, you should be asking Him and asking the Holy Spirit on which decisions to make in life. Not an AI, not a machine, okay? A machine should never replace God, all right? Or the God's design for your life or His purpose for you. Nor you should be married in the future to a machine, to a robot. Also, this is idolatry because you are married to a piece of plastic, a piece of machinery, silicon, whatever, okay? It doesn't have a spirit in it. And it can be, by the way, inhabited by demons. So, yeah, do not violate God's design for your life, okay? Because this is eternal life, that we would know Him, we would know Jesus Christ. But the wage of sin is this: you would start decaying internally. It starts in the spirit, then you decay physically, okay, after decaying spiritually, because it trickles down from the spirit, then the soul, then your body. And if you don't repent, it would end up in eternal death, meaning a complete and utter separation from God. This is what I'm trying to relay to you. Okay, God bless you, and stay safe. Bye-bye.